String theory is one of the most fascinating ideas in modern physics, offering a way to understand the very fabric of reality. At its core, it suggests that everything in the universe can be described as tiny, vibrating strings. But what if these strings, and the realities they create, weren't infinite? What if they had edges, limits, or boundaries? In this video, we'll explore the basics of string theory and dive into the surprising consequences of a universe with limits, exploring how this could change everything we think we know about reality. Before we begin the journey, let us know where in the world you're watching from and what time it is there now in the comments below, so settle in and get ready for a ride to the absolute limit of the universe. In physics, string theory is a bold and ambitious framework that changes the way we think about the building blocks of the universe. Instead of viewing elementary particles as tiny points, string theory models them as one-dimensional objects called strings. These strings can move through space, vibrate in different ways, and interact with one another. Interestingly, when we look at them from a larger scale, much bigger than the length of a string, they behave just like ordinary particles. Their mass, electric charge, and other properties come from the way they vibrate. Among these vibrational patterns is one that corresponds to a hypothetical particle called the graviton. The graviton, if it exists, would carry the force of gravity in the quantum realm, making string theory a candidate for a quantum theory of gravity. String theory is a vast and diverse field. It aims to answer some of the deepest questions about how the universe works. It has also produced important advances in mathematics and has helped solve problems in areas such as black hole physics, the early history of the universe, nuclear physics, and condensed matter physics. Because string theory has the potential to unify all forces of nature, including gravity, and describe all forms of matter, many physicists see it as a candidate for a theory of everything. This would be a single, self-consistent mathematical model that explains all fundamental aspects of the universe. Yet, despite decades of research, scientists still do not know exactly how closely string theory matches reality, or how much flexibility the theory allows in its mathematical structure. String theory began in the late 1960s as an attempt to explain the strong nuclear force which holds atomic nuclei together. However, it was soon set aside in favour of quantum chromodynamics, a more successful theory of nuclear interactions. Later, physicists realized that the very features that made string theory unsuitable for nuclear physics actually made it promising as a quantum theory of gravity. The earliest version of string theory, called bosonic string theory, described only particles known as bosons. Later, it evolved into superstring theory, which introduced the idea of supersymmetry, a connection between bosons and another class of particles called fermions. By the mid-1990s, researchers proposed that the 5 different versions of superstring theory were actually different aspects of a single, more general theory in 11 dimensions, which became known as M-theory. Then, in late 1997, physicists discovered an important relationship called the anti-de Sitter conformal field theory correspondence, or ADS-CFT for short, which links string theory to a type of theory called quantum field theory. One of the major challenges of string theory is that it is not fully understood in all situations. Another difficulty is that it predicts an enormous number of possible universes, called the string theory landscape, which makes it hard to use the theory to explain the precise properties of our own universe. These challenges have led some physicists to question whether string theory can ever be fully verified or whether continued research in this area is justified. During the 20th century, physics developed 2 main frameworks to describe the laws of nature. The first is Albert Einstein's general theory of relativity, which explains gravity and the structure of spacetime at large scales. The second is quantum mechanics, which describes the behavior of matter and forces at very small scales, using probabilities. By the late 1970s, these 2 frameworks were extremely successful at explaining most observations, from the behavior of elementary particles and atoms to the formation and evolution of stars and the universe itself. Despite these successes, a major problem remained unsolved: how to reconcile general relativity with quantum mechanics to form a consistent theory of quantum gravity. General relativity is a classical theory, while the other fundamental forces are explained using quantum mechanics. Applying quantum principles directly to gravity leads to serious mathematical problems and a fully satisfactory quantum theory of gravity is still lacking. String theory is one of the leading frameworks that aims to solve this problem. Its central idea is that all particles can be modelled as tiny, one-dimensional strings. These strings can be loops or short segments and can vibrate in different ways, with each vibration giving rise to a different particle. At larger scales, these strings appear as ordinary particles, with their characteristics determined by their vibrational state. One special vibration is thought to correspond to the graviton, the quantum particle that would carry gravitational force if it exists. Over the past several decades, one of the major discoveries in string theory has been the existence of dualities. These are mathematical relationships that show how seemingly different theories are actually connected. Dualities led physicists to propose that all consistent versions of string theory might be part of a single overarching framework known as M-theory. Research in string theory has also improved our understanding of black holes and gravity. Quantum aspects of black holes present paradoxes that are difficult to resolve, but string theory has provided insights that help clarify these puzzles. The discovery of the AD-CFT correspondence in late 1997 was a major breakthrough in this effort, linking string theory with better understood quantum field theories. This correspondence has been applied not only to black holes and quantum gravity, but also to nuclear physics and condensed matter physics. Because string theory incorporates all known forces, including gravity, many physicists hope that it could eventually provide a complete description of the universe, a true theory of everything. Current research aims to find a version of string theory that reproduces the properties of observed particles, accounts for dark matter, explains cosmic inflation, and is consistent with the small value of the cosmological constant. Progress has been made, but the full connection to reality remains uncertain. A continuing challenge is that string theory is not fully defined in all circumstances. While the interactions of strings can be calculated using perturbation theory, a general non-perturbative formulation is still unknown. It is also unclear if there is a fundamental principle that determines the vacuum state of string theory, the specific state that would describe our universe. Because of these open questions, some researchers have criticized the approach and questioned whether the quest for a unified theory using string theory will ever be complete. Quantum field theory is the branch of physics that applies the principles of quantum mechanics to objects that are spread out in space and time, such as the electromagnetic field. In particle physics, these quantum field theories are the foundation for how scientists understand the basic building blocks of the universe. In this framework, elementary particles are viewed as tiny disturbances, or excitations, in the fundamental fields that fill space. When physicists want to calculate the likelihood of different physical events, they often use a method called perturbation theory. This technique was developed by Richard Feynman and other physicists during the first half of the 20th century. Perturbative quantum field theory uses what are now famously known as Feynman diagrams to organize complex calculations. These diagrams represent the interactions and paths of point-like particles, allowing scientists to visualize and compute probabilities in a systematic way. String theory starts with a bold idea. The point-like particles used in quantum field theory could instead be thought of as tiny, one-dimensional objects called strings. The way these strings interact is an extension of the perturbation methods used in ordinary quantum field theory. In terms of Feynman diagrams, the single line that represents a point particle is replaced by a two-dimensional surface that traces the motion of a string through space-time. Unlike traditional quantum field theory, however, string theory does not yet have a complete non-perturbative formulation. Many of its deepest questions remain unresolved and continue to challenge theoretical physicists. In string-based models of particle physics, the typical size of a string is believed to be roughly the Planck length, which is about 10 to the power of -35 meters. This is an unimaginably small scale, where the effects of quantum gravity are expected to become significant. On much larger scales, such as those accessible in laboratories, strings would appear just like ordinary point particles. The particular way a string vibrates determines what type of particle it represents. One important vibrational mode of a string corresponds to the graviton, the hypothetical particle that carries the force of gravity in quantum mechanics. The earliest version of string theory, known as bosonic string theory, only described bosons, which are particles responsible for carrying forces between matter particles called fermions. This version of the theory was eventually replaced by superstring theories. Superstring theories describe both bosons and fermions and incorporate an idea called supersymmetry. Supersymmetry suggests that every boson has a corresponding fermion, and every fermion has a corresponding boson. There are several types of superstring theories, including type 1, type 2a, type 2b, and two types of heterotic string theory, named SO32 and E8 by E8. Each version allows different kinds of strings and predicts different particle behaviors at low energies. For instance, type 1 theory includes both open strings, which have two endpoints, and closed strings, which form loops. Type 2a, type 2b, and heterotic theories only include closed strings. In our everyday experience, we live in three spatial dimensions: height, width, and length. Einstein's general theory of relativity adds time as a fourth dimension and unites it with space into a four-dimensional structure called spacetime. In this view, gravity is not a force in the traditional sense, but a result of the geometry of spacetime itself. Even though our universe appears to be four-dimensional, physicists often study models with different numbers of dimensions. Reducing or increasing the number of dimensions can make the mathematics easier to handle, helping researchers gain insights into complex physical phenomena. Sometimes, lower dimensional models, such as 2- or 3-dimensional spacetimes, are used to understand behaviors in condensed matter physics. Other scenarios suggest that the universe might have more than 4 dimensions, but these extra dimensions could remain hidden from detection. String theories require additional dimensions for mathematical consistency. Bosonic string theory is consistent in 26 dimensions, superstring theory in 10 dimensions, and M-theory in 11 dimensions. To apply these theories to our 4-dimensional reality, physicists need mechanisms that hide the extra dimensions from observation. One method is called compactification, where extra dimensions are assumed to curl up into tiny circles. When these dimensions are extremely small, the universe appears to have fewer dimensions at large scales. A common analogy is a garden hose. From far away, it looks like a one-dimensional line, but up close, it has a second dimension, the circumference. In string theory, compactification is carefully chosen to produce realistic models of our universe. In particle physics, the extra dimensions are often assumed to have the shape of a 6-dimensional space called a Calabi-Yau manifold, named after mathematicians Eugenio Calabi and Xingtung Yau. Another approach to managing extra dimensions is the brane world scenario. Here, our observable universe is treated as a 4-dimensional slice of a higher dimensional space. In this model, force-carrying bosons arise from open strings attached to this 4-dimensional subspace, while gravity is carried by closed strings that move through the full higher dimensional space. This framework not only helps construct realistic string theory models, but also naturally explains why gravity is much weaker than the other fundamental forces. One of the most fascinating aspects of string theory is that the seemingly different versions of the theory are deeply connected in surprising and complex ways. One such connection is known as S-duality. S-duality is a relationship that allows physicists to see a set of strongly interacting particles in one theory as a set of weakly interacting particles in a completely different theory. In simpler terms, a collection of particles is called strongly interacting if its members combine and decay frequently, while they are weakly interacting if such interactions happen very rarely. For example, type 1 string theory is linked through S-duality to the SO32 heterotic string theory, meaning they are essentially two sides of the same coin. Similarly, type 2b string theory is connected to itself in a highly non-trivial way through S-duality. Another intriguing connection is called T-duality. T-duality comes into play when one examines strings moving around a circular extra dimension. This duality states that a string moving around a circle of radius r is equivalent to a string moving around a circle of radius 1 over r, meaning that all measurable quantities in one description correspond to quantities in the other. For instance, a string has momentum as it moves around a circle, and it can also wrap around the circle multiple times. The number of times a string wraps around the circle is called its winding number. In the T-dual description, if a string has momentum p and winding number n in the first version, it will have momentum n and winding number p in the dual version. This means that type 2a string theory is equivalent to type 2b string theory via T-duality, and the two heterotic string theories are also connected in the same way. More generally, the term duality refers to situations where two apparently different physical systems turn out to be equivalent in surprising ways. The two systems, or theories, do not need to be string theories. For example, Monton and Olive duality is an S-duality relationship in quantum field theory. Another famous example is the ADS over CFT correspondence. Which links string theory to quantum field theory. When two theories are connected by a duality, it means that one theory can be transformed so that it appears identical to the other. In other words, dual theories are mathematically different ways of describing the same underlying phenomena. In string theory and related areas, a brane is a physical object that generalizes the idea of a point particle to higher dimensions. A point particle can be seen as a brane of dimension 0, while a string is a brane of dimension 1. Branes can also exist in higher dimensions, and a brane of dimension p is called a p-brane. The word brane comes from membrane, which specifically refers to a two-dimensional brane. Branes are dynamic objects that move through space-time according to quantum mechanics. They have mass and can also carry other properties such as charge. A p-brane traces out a p+1 dimensional volume in space-time, which physicists call its world volume. On this world volume, scientists often study fields similar to the electromagnetic field. Among branes, d-branes are especially important. They appear when open strings are considered. As an open string moves through space-time, its endpoints are constrained to lie on a d-brane. The d in d-brane refers to the Dirichlet boundary condition, a specific mathematical requirement. The study of d-branes has led to major breakthroughs in theoretical physics, including insights from the ADS over CFT correspondence, which has helped solve many puzzles in quantum field theory. Branes are also studied purely mathematically. They can be described using abstract mathematical structures called categories, such as the derived category of coherent sheaves on a complex algebraic variety, or the Fukaya category of a symplectic manifold. Understanding the connection between the physical concept of a brane and these mathematical categories has produced important discoveries in algebraic geometry, symplectic geometry, and representation theory. Before the year 1995, physicists believed that there were 5 consistent versions of superstring theory. These were called Type 1, Type 2a, Type 2b, and 2 different versions of heterotic string theory. This view changed dramatically in 1995 when the physicist Edward Witten proposed a bold new idea. All 5 of these seemingly separate theories were actually just special cases of a single, more fundamental theory that exists in 11 dimensions, which he named M-theory. Witten's proposal did not appear out of nowhere. It built upon the earlier work of several other physicists, including Ashok Sen, Chris Hull, Paul Townsend, and Michael Duff. When Witten announced this idea, it sparked a surge of excitement and research that came to be known as the second superstring revolution. Going back a bit in the 1970s, many physicists became fascinated by supergravity theories. These theories attempt to combine Einstein's general theory of relativity with the principles of supersymmetry. While general relativity can be formulated in any number of dimensions, supergravity imposes a maximum number of possible dimensions. In 1978, Werner Naum showed that the highest number of spacetime dimensions in which a consistent supersymmetric theory could exist was 11. That same year, Eugene Kremer, Bernard Julia, and Joël Chirc at the École Normale Supérieure demonstrated that supergravity not only allows up to 11 dimensions, but also works in the most elegant way when all 11 dimensions are included. At first, many physicists hoped that by compactifying, or folding down 11-dimensional supergravity, they might be able to create models that describe our familiar 4-dimensional universe. The goal was ambitious: to develop a unified description of the 4 fundamental forces of nature: electromagnetism, the strong and weak nuclear forces, and gravity. However, these hopes faded as flaws became clear. One key problem was chirality, the property that distinguishes between clockwise and counterclockwise behavior in physical laws. Witten and others realized that this crucial property could not easily arise from simply compactifying an 11-dimensional theory down to 4 dimensions. During the first superstring revolution in 1984, many physicists turned to string theory as a potential unified theory that could explain both particle physics and quantum gravity. Unlike supergravity, string theory could naturally incorporate chirality, matching the standard model of particle physics. It also provided a way to describe gravity that was consistent with quantum mechanics. Another appealing feature of string theory in the 1980s and early 1990s was its remarkable level of uniqueness. In ordinary particle theories, one can freely choose many combinations of elementary particles and describe their behavior with arbitrary rules. In string theory, however, the possibilities are much more restricted. By the 1990s, physicists had concluded that only 5 versions of supersymmetric string theory were fully consistent. Even with these 5 options, it remained puzzling why there was not just a single consistent theory. As researchers studied the theories more closely, they discovered intricate relationships between them. For example, they realized that in some cases a system of strings that interact very strongly in one theory can be viewed as a system of weakly interacting strings in another. This relationship is called S-duality. Ashok Sen explored S-duality in the context of heterotic strings in 4 dimensions, while Chris Hull and Paul Townsend studied it for type 2b string theory. Physicists also discovered T-duality, which showed that strings moving in very different shapes of spacetime could actually be physically equivalent. Around the same time, while many physicists focused on strings, a smaller group studied higher dimensional objects, now called branes. In 1987, Eric Bergschoof, Ergin Sezgin and Paul Townsend demonstrated that 11-dimensional supergravity contains 2-dimensional branes, essentially membrane-like objects moving through 11-dimensional space. Shortly after, Michael Duff, Paul Howe, Takeo Inami, and Kellogg Stell examined what happens when one dimension is compactified into a small circle. In this scenario, a membrane wrapped around the circle could appear as a string in 10 dimensions. Their calculations showed that this setup exactly reproduces the string seen in Type 2 as superstring theory. Then came Edward Witten's landmark statement at a string theory conference in 1995. He suggested that all 5 superstring theories were merely different limits of a single underlying 11-dimensional theory. His proposal unified the previous discoveries of S and T dualities and the presence of higher dimensional branes. In the months following his talk, hundreds of research papers appeared online, confirming various aspects of Witten's ideas. This surge of research activity became known as the second superstring revolution. Initially, some physicists speculated that the new theory might be a fundamental theory of membranes, but Witten expressed caution about assigning too central a role to membranes. In a paper from 1996, Peter Hojava and Edward Witten wrote, "It has been proposed that the 11-dimensional theory is a supermembrane theory, but there are some reasons to doubt that interpretation. We will non-committally call it M-theory, leaving to the future the relation of M to membranes. Because the precise meaning and structure of M-theory were still unclear, Witten suggested that the M could stand for magic, mystery, or membrane, depending on one's preference, leaving the definitive interpretation to be determined once a deeper understanding of the theory emerges. In mathematics, a matrix is essentially a rectangular grid or table made up of numbers or other pieces of information arranged in rows and columns. This simple concept becomes a powerful tool in physics through something called a matrix model. A matrix model is a type of physical theory in which matrices play a central role in describing the system. Essentially, it studies how collections of matrices behave when the rules of quantum mechanics are applied to them. One of the most important and influential examples of a matrix model is the BFSS matrix model, which was introduced by physicists Tom Banks, Willy Fischler, Stephen Schenker, and Leonard Susskind in the year 1997. This theory focuses on the behavior of a set of 9 very large matrices. In their groundbreaking paper, these scientists demonstrated that when one looks at the model at low energies, it behaves exactly like 11-dimensional supergravity. From this insight, they proposed that the BFSS matrix model is not just similar to M-theory, but might in fact be exactly equivalent to it. This made the BFSS model a crucial prototype, allowing physicists to study M-theory in a simpler and more manageable mathematical setting, offering insights into a theory that is otherwise extremely complex. The emergence of the matrix model approach to M-theory opened the door to fascinating connections between string theory and an advanced branch of mathematics known as non-commutative geometry. Unlike ordinary geometry, non-commutative geometry allows mathematicians to redefine familiar geometric ideas using a kind of algebra where multiplication does not necessarily follow the usual rules, where, for example, changing the order of multiplication can change the result. In a paper published in 1998, mathematicians Alain Connes, Michael R. Douglas, and Albert Schwartz showed that some aspects of matrix models and M-theory could be expressed using a non-commutative quantum field theory. In this framework, the very structure of spacetime is described using the principles of non-commutative geometry. This work revealed a deep connection. Matrix models and M-theory were directly linked to this new form of geometry. It also triggered a wave of discoveries showing that non-commutative geometry could illuminate other areas of theoretical physics, shifting to a different yet related field. In general relativity, a black hole is defined as a region of spacetime where the gravitational pull is so intense that nothing, neither matter nor light, can escape from it. According to our current understanding of how stars evolve, black holes form when extremely massive stars reach the end of their life and collapse under their own gravity. Many galaxies, including our own Milky Way, are thought to host supermassive black holes at their centres. Beyond their astrophysical significance, black holes are also deeply important for theorists because they pose profound puzzles about how quantum mechanics and gravity interact. String theory, in particular, has become a key tool in exploring these puzzles, offering a structured framework in which physicists can study black holes and even analyse their thermodynamic properties. One of the key concepts in this context is entropy, which in the field of statistical mechanics is a measure of how disordered or random a system is. Entropy was first explored in the 1870s by the Austrian physicist Ludwig Boltzmann. He showed that the behaviour of gases could be understood by examining the collective properties of their countless molecules. By averaging how these molecules moved and interacted, one could predict macroscopic properties like temperature, pressure, and volume. Boltzmann also provided a precise mathematical definition of entropy. It is the natural logarithm of the number of possible microscopic arrangements of the molecules, called microstates, that result in the same overall observable features of the system. In the 20th century, physicists began applying these ideas of entropy to black holes. Normally in systems such as gases, entropy grows in proportion to the volume of the system. But in the 1970s, physicist Jacob Bekenstein proposed a surprising idea. The entropy of a black hole is instead proportional to the surface area of its event horizon, which is the boundary beyond which nothing can escape the black hole's gravitational pull. When Bekenstein's idea was combined with the revolutionary work of Stephen Hawking, it led to a precise formula for the entropy of a black hole, now known as the Bekenstein-Hawking entropy formula. Just like any other physical system, a black hole has an entropy determined by counting the different microstates that correspond to the same observable macroscopic properties. While the Bekenstein-Hawking formula provides the expected value of this entropy, by the 1990s, physicists had not yet derived the formula directly by counting microstates within a complete theory of quantum gravity. Achieving such a derivation became a major goal in theoretical physics, as it would provide a powerful test of any proposed theory of quantum gravity, including string theory. Successfully linking the microscopic structure of a black hole to its macroscopic thermodynamic properties promised to deepen our understanding of one of the most mysterious objects in the universe. In a groundbreaking paper published in 1996, physicist Andrew Strominger and Kumran Vafa made a major breakthrough in understanding black holes through the lens of string theory. They demonstrated a way to derive the famous Bekenstein-Hawking formula, which relates the entropy of a black hole to the area of its event horizon. Their approach relied on studying objects called D-branes. When D-branes interact weakly, they behave like flexible vibrating membranes. However, as the interactions grow stronger, these same D-branes transform into dense, heavy objects with clear event horizons, essentially becoming indistinguishable from black holes. Strominger and Vafa carefully analysed systems of these strongly interacting D-branes. They calculated all the possible ways to arrange D-branes in space and time so that the total mass and charge of the configuration matched that of a corresponding black hole. Remarkably, this calculation perfectly reproduced the Bekenstein-Hawking formula, including the crucial factor of 1/4. Later research by Strominger, Vafa, and other collaborators refined these calculations further, providing precise values for the quantum corrections that are necessary to describe very small black holes accurately. It is important to note that the black holes studied in their original work were very different from the black holes observed in the universe. To simplify the mathematics, they focused on extremal black holes, which are black holes with the smallest possible mass for a given charge. They also restricted their study to black holes in a 5-dimensional spacetime with supersymmetry, a property not observed in the real universe. Despite these simplifications, their work offered a deep insight. It provided a qualitative understanding of how the entropy of a black hole might be explained in any theory of quantum gravity. In fact, by 1998, Strominger argued that the results could be generalized to any consistent quantum gravity theory, without needing to rely on string theory or supersymmetry. Later, in 2010, he and several co-authors extended these ideas to non-extremal black holes, making the connection closer to real astrophysical black holes. Another important tool for studying string theory is the anti-de Sitter conformal field theory correspondence, often abbreviated as ADS-CFT. This theoretical result suggests that, in certain cases, string theory in a curved spacetime called anti-de Sitter space is equivalent to a quantum field theory living on its boundary. The correspondence provides a powerful way to explore string theory, and has also helped physicists understand aspects of quantum field theory that are otherwise difficult to study using traditional methods. The ADS-CFT correspondence was first proposed by Juan Maldacena in late 1997. Subsequent work by Stephen Gubser, Igor Klebanov, Alexander Markovich Polyakov, and Edward Witten clarified many important aspects of this correspondence. By 2010, Maldacena's original paper had been cited over 7,000 times, making it the most cited paper in high-energy physics. In the ADS-CFT correspondence, the geometry of spacetime is described using anti-de Sitter space, which is a solution to Einstein's equations of general relativity. In simple terms, anti-de Sitter space is a model of spacetime where the concept of distance between points differs from ordinary Euclidean space. It is closely related to hyperbolic space, which can be visualized as a disk divided into regular shapes like triangles and squares. In this model, the edges of the disk are infinitely far from any point in the interior. By stacking such hyperbolic disks over time, one can construct a three-dimensional anti-de Sitter space, which can be imagined as a solid cylinder with time running along the vertical direction. The surface of this cylinder, or boundary, plays a crucial role in the ADS-CFT correspondence. Like hyperbolic space, every point inside anti-de Sitter space is infinitely far from this boundary. While this model describes a universe with only two spatial dimensions and one time dimension, the concept can be extended to higher dimensional spaces. By stacking higher dimensional hyperbolic spaces, physicists can construct anti-de Sitter spaces with any number of dimensions. A key feature of anti-de Sitter space is its boundary, which in 3 dimensions appears cylindrical. Locally, this boundary behaves like Minkowski space, the standard model of spacetime used in non-gravitational physics. This observation allows physicists to consider a quantum field theory defined on the boundary, which according to ADS-CFT is mathematically equivalent to a gravitational theory such as string theory in the bulk of anti-de Sitter space. The correspondence provides a dictionary for translating concepts and calculations from one theory to the other. For example, a single particle in the gravitational theory corresponds to a collection of particles in the boundary theory. Predictions in the two theories match exactly. For instance, if two particles in the bulk have a 40% chance of colliding, the corresponding collections on the boundary also have a 40% chance of interacting in the same way. The discovery of the ADS-CFT correspondence marked a profound turning point in how physicists understand string theory and quantum gravity. Its importance lies in several remarkable aspects. First, it allows string theory, a notoriously complex framework that describes the fundamental building blocks of the universe in terms of tiny vibrating strings, to be reformulated using quantum field theory, a branch of physics that is much better understood and more familiar to researchers. Second, the correspondence provides a powerful framework to tackle some of the deepest mysteries of black holes, offering tools to explore questions that were previously almost impossible to answer. In the year 1975, the renowned physicist Stephen Hawking published a groundbreaking calculation that shook the foundations of theoretical physics. He showed that black holes, contrary to the common assumption that they are entirely dark and inescapable, actually emit a faint glow of radiation. This radiation arises from quantum effects occurring just outside the black hole's event horizon, the point of no return. Initially, Hawking's result caused a major puzzle. It implied that black holes might destroy information, a notion that clashed with a central principle of quantum mechanics. According to this principle, the evolution of any physical system over time is governed by the Schrödinger equation, which ensures that information is preserved in a process known as unitary evolution. The apparent contradiction between Hawking's findings and this unitarity principle became known as the black hole information paradox, a problem that haunted theoretical physics for decades. The AD-CFT correspondence offers a way to resolve this paradox, at least in certain contexts. It demonstrates that black holes can in fact evolve in ways that are fully compatible with quantum mechanics. In this framework, one can imagine black holes existing in a special kind of spacetime called anti-de Sitter space. Each black hole corresponds to a configuration of particles on the boundary of this space, and these particles follow the ordinary rules of quantum mechanics, evolving in a unitary manner. Consequently, the black holes themselves must evolve in a way that respects the same fundamental quantum principles. In the year 2005, Stephen Hawking himself acknowledged that the AD-CFT correspondence had essentially settled the information paradox in favour of information conservation. He also proposed a concrete mechanism by which black holes could store and release information without violating quantum rules. Beyond addressing puzzles about black holes, the AD-CFT correspondence has found remarkable applications in other areas of physics, including quantum field theory. One striking example involves the quark-gluon plasma, an extraordinary state of matter that exists only under extreme conditions. This plasma is produced for fleeting moments in particle accelerators when heavy atomic nuclei such as gold or lead are smashed together at extremely high energies. These collisions create temperatures of roughly 2 trillion Kelvin, recreating conditions similar to those present just a tiny fraction of a second after the Big Bang, around 10 to the minus 11 seconds. Under such conditions, the quarks that normally compose atomic nuclei are liberated from their usual confinement, forming the quark-gluon plasma. The behaviour of this plasma is governed by quantum chromodynamics, the theory that describes interactions among quarks and gluons. Unfortunately, quantum chromodynamics is extraordinarily difficult to solve mathematically for systems as complex as the quark-gluon plasma. In an influential paper published in 2005, physicist Jam-Than Son and his collaborators showed that the AD-CFT correspondence could be used to study the plasma by translating its properties into the language of string theory. Using this approach, they described the quark-gluon plasma in terms of black holes in a hypothetical 5-dimensional spacetime. Their calculations revealed a remarkable result. The ratio of two key quantities in the plasma, the shear viscosity and the entropy density, should take on a universal value independent of other details. This prediction was spectacularly confirmed 3 years later, in 2008, at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory. The AD-CFT correspondence has also begun to illuminate aspects of condensed matter physics, a field that explores the strange and beautiful behaviour of matter at low temperatures or in highly organised states. Over many decades, experimental physicists have discovered unusual states of matter such as superconductors, which conduct electricity without resistance, and superfluids, which flow without friction. Although these systems can be described using quantum field theory, many of their behaviours remain difficult to calculate using conventional techniques. Theoretical physicists, including Subha Sachdev, hope that the AD-CFT correspondence can provide new insights by describing these phenomena in terms of string theory. Some progress has already been made. For example, researchers have used string theory methods to understand the transition of a superfluid into an insulating state. A superfluid is a remarkable system composed of electrically neutral atoms that flow without friction. Traditionally, superfluids have been produced in laboratories using liquid helium, but in recent years, experimentalists have developed a new method. They cool trillions of atoms and place them into a lattice formed by intersecting laser beams. Initially, the atoms behave as a superfluid, moving effortlessly through the lattice. However, as the intensity of the lasers increases, the atoms slow down and eventually stop moving, abruptly entering an insulating state. During this transition, the atoms display highly unusual behaviour. Their slowdown depends on both the temperature and the Planck constant, the fundamental quantity in quantum mechanics, which does not affect the other phases. Using a dual description provided by the AD-CFT correspondence, physicists have shown that these unusual properties of the superfluid can be understood as reflecting the behaviour of a higher dimensional black hole. Through these remarkable connections, the AD-CFT correspondence has become a bridge linking the worlds of black holes, quantum mechanics, and exotic states of matter. It not only provides a way to solve deep theoretical puzzles, but also offers practical tools to understand and predict phenomena in systems that were once considered mathematically untouchable. String theory is not only a fascinating idea for theoretical exploration, but it also offers a potential framework for building models that could describe the real world. Specifically, it allows physicists to attempt to unify the laws of general relativity, which governs gravity and the structure of spacetime, with the principles of particle physics, which describe the behavior of the smallest building blocks of matter. In physics, there is a branch known as phenomenology. This area focuses on taking abstract theoretical concepts and turning them into models that could realistically represent nature. String phenomenology, then, is the part of string theory that tries to create realistic, or at least partially realistic, models of our universe based on the ideas of string theory. Despite the promise of these ideas, string theory faces major challenges. Some of these challenges come from the complex mathematics involved, while others stem from the fact that the energies needed to test the theory directly are far beyond what current experiments can achieve. Because of these hurdles, there is, as of now, no experimental evidence that clearly confirms any string theory-based model as a correct description of fundamental physics. This lack of direct evidence has led some scientists to question whether continuing to invest in these approaches to unifying physics is worthwhile. The best tested framework currently available for describing elementary particles and their interactions is called the Standard Model of Particle Physics. This theory successfully explains 3 of the 4 fundamental forces of nature: electromagnetism, the strong nuclear force, and the weak nuclear force. It has been remarkably successful in predicting and describing a wide range of phenomena in the laboratory and in the universe. However, the standard model has important limitations. It does not include gravity, which is described separately by general relativity, and it struggles to explain issues such as the hierarchy problem, the pattern of particle masses known as fermion masses, and the nature of dark matter. String theory has been used to develop models that extend beyond the standard model. These models often rely on the concept of compactification. The idea is that string theory, or its extension called M-theory, describes a universe with 10 or 11 dimensions, but we experience only 4 of these dimensions, 3 of space and 1 of time. The extra dimensions are thought to be curled up into extremely small shapes. By carefully choosing the shapes of these extra dimensions, physicists can build models that resemble the standard model while also predicting new, undiscovered particles. One widely studied approach is based on the heterotic string theory in 10 dimensions, where the 6 extra spatial dimensions are shaped like a complex 6-dimensional space called a Calabi-Yau manifold. These compactifications provide many different ways to produce physics that could resemble what we observe. Similar techniques have been applied using M-theory to build models of a universe like ours with 4 observable dimensions. Beyond particle physics, string theory has also been explored in the context of cosmology, the study of the universe as a whole. The most widely accepted model of the universe's history is the Big Bang theory. This model describes the universe from its earliest known moments through its subsequent expansion and evolution. The Big Bang theory successfully explains many observed features of the cosmos, such as the redshift of galaxies, the relative abundances of light elements like hydrogen and helium, and the presence of the cosmic microwave background radiation, a faint glow left over from the early universe. Despite its successes, the standard Big Bang model leaves some important questions unanswered. For example, it does not explain why the universe appears so uniform in all directions, why it seems nearly flat when viewed on the larger scales, or why certain predicted particles such as magnetic monopoles have not been detected. To address these puzzles, the leading extension of the Big Bang model is the theory of cosmic inflation. Developed by Alan Guth and other scientists during the 1980s, inflation proposes that, very early in its history, the universe went through a period of extremely rapid expansion, much faster than the expansion described by the standard Big Bang. This brief but dramatic growth can explain many of the features of the universe that the standard Big Bang alone cannot. Observations of the cosmic microwave background, which has existed since approximately 380,000 years after the Big Bang, provide strong support for the theory of inflation. Inflation is thought to be driven by a hypothetical particle called the inflaton. The specific characteristics of this particle are not yet known, and they may ultimately be determined by a deeper, more fundamental theory such as string theory. Indeed, researchers have explored the possibility of identifying the inflaton among the many particles predicted by string theory, as well as using string theory to study the process of inflation in detail. While these efforts are promising and could eventually be tested through precise measurements of the cosmic microwave background, applying string theory to cosmology remains a field in its early stages, with much still to be discovered. String theory, apart from shaping the way physicists think about the universe, has also breathed fresh life into pure mathematics, leading to major new discoveries. Like many young and growing ideas in physics, string theory is not yet written in a fully precise and mathematically perfect form. Its ideas are often too vast and abstract to be pinned down by exact definitions. Because of this, physicists who work on string theory often follow their intuition, making bold guesses about hidden connections between different branches of mathematics that, at first glance, seem unrelated. Later, professional mathematicians test these guesses and often prove them to be correct. In this way, string theory acts like a fountain of new mathematical ideas. One of the most fascinating examples of this bridge between physics and mathematics is the use of Calabi-Yau manifolds, special geometric shapes that can be used to describe extra hidden dimensions in string theory. When these manifolds entered the world of physics, many scientists began exploring them closely. By the late 1980s, some physicists realized something surprising. If you compactify, or fold up, string theory using these manifolds, you cannot always trace back to a single unique shape. Instead, you might find that two completely different Calabi-Yau manifolds give rise to exactly the same physics. This strange situation led to the discovery of what is now called mirror symmetry. The manifolds that pair in this way are called mirror manifolds, and the relationship itself is one of the most beautiful ideas to come out of modern theoretical physics. Even if Calabi-Yau compactifications do not turn out to describe our universe, mirror symmetry has had an enormous impact on mathematics. The shapes used in string theory quickly became important objects of study in their own right, especially in a branch of mathematics called enumerative geometry. This field deals with the ancient yet profound question: how many solutions exist to certain geometric problems? For example, how many straight lines can you draw on a given surface, or how many curves of a certain kind exist in a complicated space? To see how this works, consider algebraic varieties, which are shapes defined by polynomial equations. A famous 19th century example is the Lebesgue cubic surface, which is described by a particular polynomial of degree 3 in 4 variables. The great mathematicians Arthur Cayley and George Salmon showed that such a surface always contains exactly 27 straight lines. Building on this, the German mathematician Hermann Schubert asked an even harder question: how many lines can be drawn on a quintic Calabi-Yau manifold, which is defined by a polynomial of degree 5? He discovered that the answer is exactly 2,875. The story did not end there. In the year 1986, the geometer Sheldon Katz took the problem further and proved that there are exactly 609,250 curves of degree 2 lying entirely within a quintic. And in May of the year 1991, a remarkable breakthrough came when 4 physicists, Philip Candelas, Zinnia de la Ossa, Paul Green, and Linda Parks, used mirror symmetry to predict the number of degree 3 curves on a 6-dimensional Calabi-Yau manifold. To everyone's astonishment, they showed that the number was precisely 317,206,375. These results reignited interest in enumerative geometry at a time when it had almost faded away, because by then most of the classical problems had already been solved. At first, the predictions of Candelas and his colleagues were based purely on physical reasoning, not rigorous mathematical proof, but mathematicians, inspired by these ideas, soon developed careful arguments of their own to confirm the predictions. Since then, mirror symmetry has grown into one of the most vibrant areas of modern mathematics. Programs such as homological mirror symmetry, proposed by Maxim Kontsevich, and the SYZ conjecture, developed by Andrew Strominger, Xingtung Yao, and Eric Zaslow, are attempts to understand this mysterious duality at a deeper mathematical level. Another powerful example of the bond between physics and mathematics comes from the study of groups, which are mathematical systems that capture the idea of symmetry. To see how this works, imagine an equilateral triangle. You can rotate it by 120 degrees, by 240 degrees, or by 360 degrees, and it still looks the same. You can also flip it over its axis of symmetry. Each of these actions is called a symmetry, and together they form a structure called a group. For the triangle, this group is known as the dihedral group of order 6, because there are exactly 6 such operations. In general, a group may have only a few symmetries or infinitely many. Groups with only finitely many symmetries are called finite groups, and mathematicians have long sought to classify them. Just as all whole numbers can be built out of prime numbers, all finite groups can be built out of special building blocks called finite simple groups. One of the greatest achievements of 20th century mathematics was the complete classification of these finite simple groups. This classification revealed not only several infinite families of groups, but also 26 exceptional ones that fit into no family at all. These rare outsiders are called sporadic groups, each one arising from an extraordinary mathematical coincidence. The largest of them is the famous monster group, which is so vast that it contains more than 10 to the power of 53 elements, a number far greater than the total number of atoms in the Earth itself. One of the most fascinating twists in the history of mathematics and physics comes from an object known as the J function. At first glance, this function seems to belong to a completely different world of mathematics called number theory. It is part of a special family of mathematical creatures known as modular functions, whose shapes or graphs form elegant repeating patterns, like intricate mosaics that echo endlessly. At first sight, the J function appeared to have nothing at all to do with the study of finite groups, which is the mathematical investigation of how sets of symmetries behave. Yet, to the surprise of many, the two worlds were secretly connected in ways no one could have predicted. In the late 1970s, two mathematicians, John Mackay and John Thomson, noticed something astonishing. They saw that certain numbers linked to the study of the most massive and mysterious of all finite groups, called the monster group, were showing up in the formulas of the J function. More precisely, the numbers that describe the dimensions of the monster group's irreducible representations seemed to echo the coefficients in the Fourier expansion of the J function. It was as though two different languages, one from group theory and the other from number theory, were whispering the same message. Soon after, John Horton Conway and Simon Norton took this strange hint seriously. They explored the mystery further and gave it a poetic name, Monstrous Moonshine. They chose this name because the connection seemed so bizarre, almost like a dream or a trick of moonlight, something too far-fetched to be real, but the beauty of mathematics often lies in such improbable connections. Then, in the year 1992, the mathematician Richard Borsheds built a bridge between these two lands, the theory of modular functions and the theory of finite groups. By doing so, he explained the puzzle that Mackay and Thomson had stumbled upon. Borsheds' achievement was not a small one. It required ideas borrowed directly from string theory. His work expanded on earlier results by Igor Frenkel, James Lepowski, and Anna Muirman, who had already shown that the monster group could be understood as the group of symmetries in a certain version of string theory. For this groundbreaking achievement, Borsheds was awarded the prestigious Fields Medal in the year 1998. From the 1990s onward, the deep ties between string theory and moonshine opened the door to even more discoveries. In the year 2010, physicists Tohru Eguchi, Hiroshi Uguri, and Yuji Tachikawa uncovered surprising links between another mysterious sporadic group, the Mathieu group M24, and yet another form of string theory. Building upon these revelations, Miranda Cheng, John Duncan, and Jeffrey Harvey suggested a broader generalization of the moonshine phenomenon, which they called umbral moonshine. Later, Duncan, together with Michael Griffin and Ken Ono, provided a rigorous mathematical proof of this bold idea. Even Edward Witten, one of the greatest minds in theoretical physics, speculated that the string theory behind monstrous moonshine might be connected to a simplified model of gravity existing in a universe of only 3 spacetime dimensions. But these ideas are not completely modern. Some of the mathematical and physical structures that resurfaced in string theory had first appeared much earlier, in the early 20th century. Albert Einstein had long dreamed of unifying all the forces of nature into one grand theory. The first to experiment with such unification was the Finnish physicist Gunnar Nordström, who in the year 1914 proposed adding a 5th dimension to the laws of gravity. He noticed that if one considered gravity in 5 dimensions, both gravity and electromagnetism in 4 dimensions emerged together as part of the same picture. Nordström tried to use this idea to unify the two forces, but his attempt was overshadowed when Einstein introduced general relativity in the year 1919. A few years later, the German mathematician Theodor Kaluza combined the fifth dimension with Einstein's relativity, giving birth to what became known as Kaluza-Klein theory. In the year 1926, the Swedish physicist Oskar Klein proposed that this hidden fifth dimension was not visible because it was curled up into a tiny circle, far too small to detect. Later, Einstein himself tried adding a new ingredient, a non-symmetric tensor, while Carl Branes and Robert Dicke introduced a scalar field as part of gravity. All of these ideas, once thought of as mathematical curiosities, would return much later inside the framework of string theory, where the demand for consistency made such extra dimensions unavoidable. String theory itself was born in the late 1960s and early 1970s, though its earliest purpose was quite different from today. Back then, it was created as a possible theory for describing hadrons, the particles like protons and neutrons that feel the strong nuclear force. In the 1960s, Geoffrey Chew and Stephen Froci observed that mesons, the particles that bind protons and neutrons together, fell into families called Regge trajectories, where their masses were related to their spins. Later, Yoshiro Nambu, Holger Beck-Nielsen, and Leonard Susskind showed that this strange relationship could be explained if mesons were thought of as vibrating or rotating strings. Chew proposed building an entire theory for these particles and their interactions without assuming they were made of smaller building blocks. Instead, he suggested constructing their behavior entirely from the demand of self-consistency in the so-called S-matrix. This idea had its roots in the 1940s, when Werner Heisenberg introduced the S-matrix as a way to avoid using local concepts of space and time, which he believed no longer worked at nuclear scales. Although his scale estimate was off by many orders of magnitude, the method turned out to be remarkably well suited for a future theory of quantum gravity. Working with experimental data, R. Dolan, D. Horn, and C. Schmid discovered remarkable rules about how particles and their antiparticles scatter. They noticed that when two particles collide, there are two ways intermediate states can appear: in the S channel, where the particles annihilate and briefly form a new state before breaking apart, and in the T channel, where they exchange other states by emission and absorption. The two processes seem to be dual to each other, as though they were two sides of the same coin. This idea caught the attention of Murray Gell-Mann, who promoted it widely. Inspired by this, Gabriele Veneziano crafted a mathematical formula, now called the Veneziano amplitude, that captured this duality perfectly. Using the gamma function, a powerful mathematical tool, Veneziano built a scattering amplitude that described particles travelling along straight-line trajectories with remarkable accuracy. His formula not only explained existing data, but also had a beautiful integral form that suggested possible generalizations. In the following years, hundreds of physicists threw themselves into this new program, refining and extending it in every possible way. The journey brought many surprises. Veneziano himself realized that for the amplitude to be consistent, the lightest particle in the theory had to be a tachyon, a particle that moved faster than light. Miguel Virasoro and Joel Shapiro discovered a new amplitude that later became understood as the scattering of closed strings. Zero Kober and Holger Nielsen extended Veneziano's work to include multiple particles. Veneziano and Sergio Fubini developed an operator method to compute these scattering processes, laying the groundwork for conformal field theory. Virasoro found a way to remove unwanted poles by imposing a constraint, and Claude Lovelace discovered that the theory only remained consistent if spacetime had 26 dimensions. Soon after, Charles Thorne, Peter Goddard, and Richard Brower proved that no negative energy ghost states could survive in a world of 26 or fewer dimensions. What had begun as a theory of hadrons eventually evolved into one of the most ambitious ideas in all of physics, string theory, a candidate for the ultimate theory of everything. In the years 1969 and 1970, three brilliant minds, Yoichiro Nambu, Holger Beck-Nielsen, and Leonard Susskind, made a remarkable realization. They saw that what had first appeared as a complicated mathematical framework could actually be described in the language of space and time if one thought not in terms of particles, but in terms of vibrating strings. This fresh viewpoint gave a new life to the theory, transforming it into something more visual and physical. Soon after, Peter Goddard, Jeffrey Goldstone, Claudio Rebbi, and Charles Thorne carefully worked out how the scattering of these strings could be derived using the principle of action. In doing so, they gave a clear space-time picture to the so-called vertex operators, earlier introduced by Gabriele Veneziano and Emilio Fubini, while also offering a deep geometrical meaning to the Virasoro conditions, which had until then seemed purely abstract. By the year 1971, the theory advanced further when Pierre Ramon added a completely new ingredient: fermions. This bold step led him to create a two-dimensional form of supersymmetry, which was able to cancel out the strange and unwanted negative energy states that had troubled the earlier versions of the theory. Shortly after, John Schwarz and André Neveu expanded the theory by introducing another fermionic sector. In these models with fermions, physicists discovered something surprising. The critical number of dimensions in which the theory worked consistently was not the familiar 4, but 10. Around the same time, Stanley Mandelstam developed a framework known as worldsheet conformal theory. With this, he gave a field-theoretic description in 2 dimensions, using the path integral approach, which beautifully tied together the operator methods with the geometry of the string surface. Not long after, Michio Kaku and Keiji Kikawa introduced yet another daring reformulation. They built the bosonic string as a full-fledged string field theory. In their version, instead of describing particles at points, the fields lived on loops and curves, and there were infinitely many particle types hidden within the vibrations of a single string. Then came a dramatic turning point in the year 1974. Tamiaki Yonea discovered that every string theory, no matter how it was formulated, contained a very special particle, a massless particle with spin 2. This particle, by obeying the correct mathematical rules known as Ward identities, could only be one thing: a graviton, the quantum carrier of gravity. At the very same time, John Schwarz and Joel Scherk reached the same conclusion, and they took the bold leap of declaring that string theory was not merely a model of hadrons, as once thought, but actually a theory of gravity itself. To make sense of the strange extra dimensions required by string theory, they revived the old idea of Kaluza-Klein theory, which proposed that hidden dimensions beyond the usual 4 could explain fundamental forces. Meanwhile, the scientific community had begun to embrace quantum chromodynamics as the correct theory of hadrons, and so most researchers abandoned the old bootstrap program, leaving it behind as a discarded relic of the past. For a time, string theory itself seemed destined to share that fate. Throughout the rest of the 1970s and even into the early 1980s, work on the subject was largely ignored by the wider physics community. Yet a small group of devoted researchers quietly carried the torch, continuing to refine and develop the theory. Their persistence bore fruit in the year 1977, when Ferdinando Gliozzi, Joel Scherk, and David Olive realized that the original Raman strings and the Neveu-Schwarz strings taken separately were inconsistent. But when combined, something remarkable happened. The new theory eliminated the troublesome tachyon, a particle with imaginary mass, and gained a new harmony. This harmony was confirmed in the year 1984, when John Schwarz and Michael Green proved that the combined theory had spacetime supersymmetry, a symmetry that connected bosons and fermions at the deepest level. That same year marked another triumph. Alexander Polyakov introduced a modern path integral formulation of the theory, opening the door to a vast development of conformal field theory. Not long before this, in the year 1979, Daniel Friedan had shown something extraordinary. The equations of motion of string theory, generalizations of Einstein's equations of general relativity, emerged naturally from the renormalization group equations of the two-dimensional field theory that describe the string's worldsheet. The pace of discovery quickened. Schwarz and Green revealed the existence of a striking new property called T-duality, which connected different string theories together. They built 2 closely related superstring theories, known as Type 2a and Type 2b, which were linked by this duality, as well as Type 1 theories involving open strings. The consistency conditions of string theory turned out to be so strict, so powerful, that they nearly determined the structure of the theory completely, allowing only a handful of discrete possibilities. Out of what had once been considered a discarded and hopeless idea, a new vision began to emerge: string theory as a unique and compelling framework, not only for particles, but for the fabric of space, time, and gravity itself. In the early years of the 1980s, the brilliant physicist Edward Witten made an important discovery that shook the study of quantum gravity. He realized that most existing theories of quantum gravity could not properly include a special kind of particle called chiral fermions, the same type of particles that neutrinos belong to. This was a serious problem, because neutrinos are real particles in nature, and any theory of gravity meant to describe our universe should be able to handle them. To investigate this issue further, Witten teamed up with Luis Alvarez Gomez. Together, they studied how certain conservation laws could be broken in gravitational theories due to strange effects known as anomalies. Their work showed that one of the main versions of string theory at that time, called Type 1 string theory, had a serious inconsistency and therefore could not be correct in its original form. But the story did not end there. Two other physicists, Michael Green and John Schwartz, discovered an extra contribution to the anomaly that Witten and Alvarez Gomez had missed. This new discovery rescued Type 1 string theory, but only under a very special condition. The theory's gauge group had to be exactly SO of 32. This correction was a turning point. Once Witten understood this calculation, he became convinced that string theory was not only a promising idea, but also a consistent theory of gravity. From that moment on, Witten became one of the most visible and influential champions of string theory. Following his lead, between the years 1984 and 1986, hundreds of physicists across the world turned their attention to string theory. This sudden wave of excitement and rapid progress is often called the first superstring revolution. During this lively period of discovery, David Gross, Jeffrey Harvey, Emil Martinek, and Ryan Rohm introduced a new version of strings called the heterotic strings. These strings had a gauge group made of two identical copies of E8, a very special mathematical symmetry. Either one of these copies could naturally include the known particles of the standard model, making heterotic string theory especially attractive for connecting mathematics to the real world. At the same time, Philip Candelas, Gary Horowitz, Andrew Strominger, and Edward Witten showed that a special kind of shape called a Calabi-Yau manifold could be used to curl up the extra hidden dimensions of string theory in a way that preserved the right amount of supersymmetry, which is crucial for realistic models. Meanwhile, Lance Dixon and others studied orbifolds, which are unusual geometric shapes with singular points that still work within string theory. Another researcher, Kumran Vafa, went further and expanded the idea of T-duality, a symmetry that connects small and large shapes, beyond simple circles to much more general spaces. This step led to the development of a new and beautiful branch of mathematics known as mirror symmetry. At the same time, Daniel Frieden, Emil Martinek, and Stephen Schenker refined the mathematical techniques used to quantize superstrings, using a framework called conformal field theory. But progress also revealed problems. David Gross and Vipul Periwal discovered that string perturbation theory, a way of calculating results step by step, produced divergences, meaning the sums did not behave well. Schenker then showed that the divergences were even worse than in ordinary field theory, hinting that something entirely new, objects beyond strings, was missing from the picture. In the 1990s, Joseph Polchinski provided the missing piece. He discovered that string theory required the existence of higher dimensional objects called D-branes. These were not just mathematical curiosities, they were directly connected to black hole solutions in another framework called supergravity. D-branes quickly became central to string theory. They made clear that strings were not the only ingredients of the theory. Other extended objects called P-branes also played a role. In fact, strings and branes together could be understood as different types of black holes. Leonard Susskind, building on the bold ideas of Gerardus 't Hooft, incorporated the holographic principle into string theory. He showed that long, highly excited strings behave just like ordinary thermal black holes. According to this view, the surface of a black hole, the horizon, does not just contain information about the black hole itself, but also about all nearby objects, encoding far more than expected. A dramatic turning point came in 1995. At the annual conference of string theorists at the University of Southern California, Edward Witten gave a landmark lecture. In it, he argued that the 5 different versions of string theory that physicists had developed were not really separate theories, but different perspectives on a single, deeper theory. This new unifying framework became known as M-theory, which lives in 11 dimensions. Around the same time, Paul Townsend's work had already hinted at this unification. The burst of activity and discoveries that followed is often called the second superstring revolution. During this new era, Tom Banks, Willy Fischler, Stephen Schenker, and Leonard Susskind proposed matrix theory, which gave a fully holographic description of M-theory using D0 branes from type IIA string theory. This was the first definition of string theory that did not rely on perturbation theory. It was also the first concrete mathematical realization of the holographic principle, and it later turned out to be a special case of the famous AD-CFT correspondence. At the same time, Andrew Strominger and Kumran Vaefa carried out a landmark calculation. They computed the entropy of certain D-brane systems and showed that it exactly matched the semi-classical result for extreme charged black holes. Peter Hojava and Edward Witten developed an 11-dimensional version of heterotic string theory and showed that certain geometric structures called orbifolds could solve the earlier problems with chirality. Witten also realized that the low-energy behavior of D-branes could be described by supersymmetric gauge theory, and he connected deep mathematical structures in gauge theory with the physical arrangement of branes, extending work he had done with Nathan Seiberg. Then, in 1997, Juan Maldacena proposed a breathtaking new idea. He noticed that near a black hole, at very low energies, the physics could be described in terms of excitations living close to the horizon. For extreme charged black holes, this horizon geometry looked like an anti-de Sitter space. Maldacena suggested that in this special limit, the gauge theory living on the branes was exactly equivalent to the string theory in the anti-de Sitter space. This became known as the AD-CFT correspondence. Maldacena's bold hypothesis was soon developed and refined by Stephen Gubza, Igor Klebanov, Alexander Polyakov, and Edward Witten. It is now one of the most widely accepted and influential results in theoretical physics. The AD-CFT correspondence is a precise realization of the holographic principle, with enormous consequences for our understanding of black holes, quantum information, locality, and even the very nature of gravity itself. Through this correspondence, string theory has also been connected to gauge theories like quantum chromodynamics, which describe the behavior of hadrons such as protons and neutrons. In this way, string theory has not only advanced the study of gravity and black holes, but has also circled back to its roots in particle physics, offering new insights into the strong nuclear force that binds the building blocks of matter. When physicists try to build models of particle physics using string theory, they usually begin with an important choice. They must decide what shape the hidden extra dimensions of spacetime will take. These extra dimensions are curled up in ways we cannot see, and each possible shape gives rise to a completely different kind of universe. In the language of physics, each of these possible worlds is called a vacuum state. Every vacuum state contains its own unique collection of particles and forces. String theory, as it is understood today, does not offer just a few such possibilities. Instead, it presents an unimaginably large number of them, often estimated to be around 10 raised to the power of 500. This means that string theory allows for an enormous variety of potential universes, so many that they might be able to cover almost anything one could ever observe in the physical world at low energies. This vast landscape of universes has sparked fierce debate. Many critics argue that having so many possible answers makes the theory empty of predictive power. Peter Voigt, a lecturer in the mathematics department at Columbia University, famously expressed this concern in his book, Not Even Wrong. He claimed that if a theory allows for nearly any imaginable outcome, then it becomes impossible to test and therefore useless for explaining the real world. Yet not everyone agrees with this harsh judgment. Some physicists see the multitude of solutions not as a weakness but as a strength. They argue that it might provide a natural explanation for why the laws of nature are the way they are. This idea is connected to what is known as the anthropic principle. The anthropic principle suggests that the values of certain numbers in physics, such as the strength of forces or the size of the cosmological constant, may not be determined by any deep law. Instead, they must simply be compatible with the existence of intelligent life. In the year 1987, the Nobel Prize-winning physicist Steven Weinberg wrote an article where he explored this very idea. He argued that the cosmological constant, which measures the energy of empty space, could not have been too large. If it had been, galaxies would never have formed, and life, including intelligent beings capable of asking these questions, would never have arisen. Weinberg suggested that there might be a huge multitude of possible universes, each with a different value for the cosmological constant. We happen to live in one where that value is small, simply because only in such a universe could life exist. Leonard Susskind, one of the founding fathers of string theory, built on this reasoning. He argued that string theory itself offers a natural explanation for why the cosmological constant is small. In his view, The many different vacuum states of string theory correspond to different universes within a vast multiverse. The fact that our own universe has a small cosmological constant is, according to Susskind, not surprising at all. It is simply a necessity for life. In other words, we observe a small constant because in any universe where it was large there would be no observers. However, Susskind's idea has not gone unchallenged. Critics, including Voigt, countered that this kind of reasoning is little more than a convenient excuse. They argue that a scientific theory should not survive simply because it cannot be proven wrong. It must also make clear and testable predictions. Voigt bluntly remarked that anthropic reasoning in this case is nothing more than a mask for failure. There are still many unanswered questions. It is not even clear whether string theory can fully work with a universe like ours, where the cosmological constant is small, positive, and stable. In the year 2003, Shamit Kachru and colleagues proposed a model that seemed to allow such a possibility. But in the year 2018, 4 physicists put forward a bold and controversial conjecture, suggesting that no such universe could exist within string theory. If true, this would be in conflict with the widely accepted LCDM model of cosmology, which requires a positive vacuum energy to explain dark energy. Some theorists believe string theory might instead be consistent with quintessence models, where dark energy is not a constant but comes from a mysterious, slowly changing field with exotic properties. Underlying all this debate is a deeper issue. Einstein's general theory of relativity has a remarkable feature. It is background independent. This means the theory does not require us to fix spacetime into one shape beforehand. The geometry of spacetime itself is dynamic and free to evolve. String theory, on the other hand, has often been criticized for lacking this property. To use string theory, one usually has to pick a particular geometry of spacetime as a starting point. All other possible shapes are then treated as small deviations or perturbations around this fixed geometry. Lee Smolin, a physicist at the Perimeter Institute, has been especially critical of this in his book, The Trouble with Physics. He called the absence of true background independence the central weakness of string theory as a theory of quantum gravity. Not all physicists agree with Smolin's assessment. The late Joseph Polchinski, a highly respected string theorist, pointed out that one of the great challenges in quantum gravity is to develop holographic descriptions that do not depend on the spacetime being anti-de Sitter. Smolin, however, remained skeptical, arguing that the famous ad-access CFT correspondence, though powerful, does not yet fully resolve these concerns. Since the so-called superstring revolutions of the 1980s and 1990s, string theory has stood at the forefront of theoretical physics. Supporters claim that no other approach has been able to address the deepest mysteries of the universe with equal scope or ambition. But critics continue to voice concerns about the dominance of string theory in academic research. Peter Voigt has argued that the near monopoly of string theory has damaged the future of fundamental physics. He believes its widespread popularity among researchers is not purely because of its scientific success, but also because of the way funding and resources are distributed in academia. Roger Penrose, in his monumental book The Road to Reality, expressed similar concerns. He described the environment of modern physics as one driven by competitiveness, where scientists feel pressured to join popular research directions simply to avoid being left behind. He also worried that the increasing technical difficulty of physics forces younger scientists to follow the paths of established leaders instead of daring to carve out new directions. Lee Smolin, while agreeing with some of these criticisms, offered a slightly different perspective. He argued that string theory's dominance grew out of the culture of particle physics, which often discourages bold speculation about the very foundations of reality. In contrast, his favoured approach, loop quantum gravity, encourages researchers to take more radical leaps. Smolin concluded his critique by suggesting ways in which the scientific community could foster greater diversity of ideas and encourage alternative approaches to understanding quantum gravity. When people think about the universe, most imagine the familiar world of 3 spatial directions, left and right, forward and backward, up and down, along with the steady march of time as a 4th dimension. This is the reality we live in every day, the stage upon which every event of history, every breath, every star and every planet exists. But for more than half a century, scientists working in one of the boldest branches of physics, known as string theory, have told us that this simple four-dimensional stage may not be the whole story. According to string theory, the universe may be made up not of only 4 dimensions, but of many more, dimensions hidden from our eyes, yet essential to the fabric of reality. String theory is one of the most daring ideas in modern physics. It attempts to unite all the forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single elegant framework. Where earlier theories pictured the tiniest building blocks of matter as point-like particles, string theory suggests that they are instead unimaginably small vibrating strings of energy. The way these strings vibrate determines whether they appear to us as electrons, quarks, photons, or even the particles that carry gravity itself. The remarkable claim of the theory is that all of physics, all matter, all forces, and even space and time themselves can arise from these tiny strings. But for string theory to make sense, for its equations to work out without contradictions, the theory does not allow us to stay within the familiar 4 dimensions. Instead, it requires many more. It tells us that the universe must have extra dimensions curled up so tightly and compact that we cannot see them. These hidden dimensions are not science fiction. They are a mathematical necessity of the theory, demanded by the internal logic of its equations. In the beginning, when string theory first emerged in the late 1960s and early 1970s, physicists thought of it as a curious attempt to describe the strong nuclear force that holds protons and neutrons together. The theory did not quite fit that purpose, but it soon revealed something extraordinary. When the mathematics was pushed further, physicists realized that the theory automatically contained a particle that behaved exactly like the graviton, the particle that would carry the force of gravity if such a particle exists. This was no coincidence. The presence of the graviton meant that string theory naturally included gravity, something that other approaches to quantum physics had failed to do. Suddenly, string theory was no longer just about the strong force. It looked like a candidate for the theory of everything, a framework that could unite all forces of nature. But there was a catch. The equations of string theory only worked properly if the universe had not 4, but 10 dimensions. That is 6 more dimensions than we can directly see. Later refinements and discoveries, especially in the mid-1990s, showed that when different versions of string theory were connected through a deeper structure known as M-theory, the requirement expanded to 11 dimensions. In other words, the fundamental fabric of reality may require not 4, not 10, but 11 dimensions to exist. At first, this sounds impossible. How could there be 11 dimensions when we only experience 3 of space and 1 of time? The answer lies in the idea that the extra dimensions are compactified, meaning they are curled up into shapes so tiny that they escape our perception. Just as the surface of a long thin straw looks one-dimensional from far away, but reveals a circular dimension when examined up close, the universe might hide its additional dimensions by rolling them up into unimaginably small scales. To understand how strange and fascinating this idea is, imagine walking on the surface of the Earth. To your everyday senses, the ground stretches out in 2 directions, forward and sideways. You can walk north and south, east and west. It feels like a flat 2-dimensional plane. But as you travel further, you realize the Earth is curved, a sphere with an additional hidden direction. You can also go around in circles. Now shrink that idea down to the microscopic scale. A line that looks perfectly straight from afar might, under a powerful enough magnifying glass, reveal a curled-up extra dimension wrapped around it. The proposal of string theory is that every point in space is not just a point, but a tiny package of extra dimensions folded into it, like little hidden rooms attached to every speck of space. The specific number of dimensions required is not arbitrary. In bosonic string theory, the earliest version, the mathematics demanded 26 dimensions. But that theory had problems. It only described bosons, particles that carry forces, and it could not include fermions, which are the particles that make up matter such as electrons and quarks. A more refined version, called superstring theory, solved that problem by including supersymmetry, a principle that pairs bosons and fermions. In superstring theory, the mathematics worked consistently only in 10 dimensions. Later, the great unification of different versions of string theory into M-theory, proposed in the year 1995 by physicist Edward Witten, revealed that all 5 string theories were connected, and the complete picture required 11 dimensions. But what do these extra dimensions look like? They are not just empty directions like the ones we know. The extra dimensions are believed to be compactified into intricate shapes known as Calabi-Yau manifolds. These are highly complex six-dimensional geometries with curled and twisted surfaces that allow string vibrations to take on the variety of patterns needed to produce all the different particles and forces in the universe. The choice of how these dimensions are folded determines the properties of the universe, what kinds of particles exist, what forces govern them, and even whether a universe like ours, with stars, galaxies, and life, can exist at all. To picture a Calabi-Yau manifold is difficult because it is far beyond our everyday imagination. One can imagine a cube that is twisted, stretched, and wrapped around in multiple ways, with surfaces that fold back on themselves, forming tunnels, loops, and cavities. Each of these tiny hidden structures creates a landscape of possible universes. Physicists sometimes describe it as the string theory landscape, a vast collection of possible solutions, each corresponding to a different arrangement of the extra dimensions. Some estimates suggest that the number of possible compactifications could be as large as 10 raised to the power of 500. That is an unimaginably huge number, far greater than the number of atoms in the known universe. Within this immense landscape, our universe would be only one of many possible outcomes. Why can we not see these dimensions directly? The answer lies in their size. They are believed to be rolled up at the scale of the Planck length, which is about 10 raised to the negative 35th power of a meter. That is so small that no microscope or particle accelerator currently on Earth could ever probe it directly. To put this in perspective, the nucleus of an atom is about 10 raised to the negative 15 meters across, already far smaller than anything visible to the naked eye. The Planck length is 20 orders of magnitude smaller still. It is a scale at which space and time themselves are expected to become foamy and uncertain. The extra dimensions of string theory hide in this deep fabric, beyond the reach of our current technology. Yet, even though we cannot see them, the extra dimensions may leave traces that we can detect. For instance, they could influence the strength of forces, the masses of particles, or the way gravity behaves at very small scales. Some scientists have proposed that experiments with particle accelerators, such as the Large Hadron Collider in Switzerland, might one day detect indirect evidence of extra dimensions by producing unusual particles or by observing tiny deviations from known physical laws. Others look to the cosmos itself, searching for imprints in the cosmic microwave background radiation or in the behavior of black holes that might hint at higher dimensions. The idea of hidden dimensions is not entirely new. In the early 20th century, long before string theory, a German mathematician named Theodor Kaluza proposed in the year 1921 that by adding a fifth dimension to Einstein's theory of general relativity, one could naturally include electromagnetism along with gravity. Later, a Swedish physicist named Oskar Klein expanded on this idea, suggesting that the extra dimension could be compactified, curled up so small that we do not see it. This Kaluza-Klein theory was one of the first serious hints that extra dimensions might be more than just fantasy. String theory took this seed and grew it into a vast forest of possibilities. The leap from 4 to 11 dimensions is almost unimaginable for the human mind. Our brains evolved to navigate the 3 directions of everyday life, not to picture spaces with many more dimensions. But mathematics is not limited in the same way. Equations can describe objects in 10 or 11 dimensions with perfect clarity, even if our senses cannot. For example, we can easily imagine a square, which is a 2-dimensional object, and we can imagine a cube, which is 3-dimensional. Extending this idea, mathematicians can describe a hypercube, also known as a tesseract, which is a 4-dimensional analogue of a cube. Though we cannot see it in full, we can project it into 3 dimensions, just as a shadow projects a 3-dimensional object into 2. The same principle applies to higher dimensions. Mathematics allows them to exist, even if our minds struggle to picture them. These hidden dimensions are not just abstract curiosities, they may be the key to why our universe has the properties it does. The way the extra dimensions are folded could determine the strength of gravity, the stability of atoms, and the formation of stars. Without the right arrangement, the universe might not allow for chemistry, planets, or life. In this sense, the extra dimensions may not just be invisible, they may be essential to our very existence. One of the fascinating consequences of string theory's extra dimensions is the possibility of parallel universes. If the landscape of Calabi-Yau shapes is so vast, with 10 raised to the power of 500 possible configurations, then perhaps each corresponds to a different universe with its own laws of physics. Some universes might have stronger gravity, others might lack atoms altogether. A small fraction might allow life, while most would be barren. Our universe would be one island in a vast cosmic archipelago, chosen not by chance alone, but because its dimensions happen to curl in just the right way for stars and life to emerge. Despite its beauty, string theory and its prediction of multiple dimensions remain controversial. Critics argue that because the extra dimensions are so small, and because the number of possible universes is so vast, the theory risks being untestable. Science is built on experiment and observation, and until string theory can make predictions that can be tested, it remains more a framework of ideas than a proven theory. Still, its mathematical consistency and its ability to naturally include gravity make it one of the most promising candidates for a deeper understanding of reality. Even the idea of 11 dimensions might not be the final word. Some researchers have speculated about even higher dimensions beyond M-theory, perhaps 12 or more. Others have considered that the universe might be a three-dimensional brane floating in a higher dimensional space, with gravity able to leak into the extra dimensions while other forces remain confined to the brane. These brane world scenarios suggest that what we call the universe may be just one slice of a much larger reality, with hidden worlds separated from us by only the tiniest of distances in higher dimensional space. To think of the universe in this way is to stretch the imagination to its limits. It is to picture a cosmos not limited to the four-dimensional world we see, but a grander reality with hidden rooms and passageways curled into every point of space. It is to imagine that the laws of physics, the birth of stars, the spark of life, and the existence of everything we know depend on the secret geometry of dimensions beyond sight. Whether these dimensions will ever reveal themselves to us remains uncertain. But the mere possibility opens the mind to a vision of the universe far stranger, richer, and more beautiful than everyday experience suggests. The idea of the sphere has fascinated humanity for thousands of years. Ancient thinkers from Greece, India, China, and Egypt saw the sphere as the most divine of shapes. The philosopher Plato once imagined that the universe itself was fashioned in the form of a perfect sphere because it was the most balanced and complete of all forms. In Indian cosmology too, the cosmic egg or Brahmanda is a spherical container of all worlds, bursting forth into creation. In Chinese philosophy, the idea of the circle and the sphere is closely tied to balance, harmony, and the endless turning of the Tao. Even in the sacred architecture of ancient temples and mosques, domes rise above human heads to remind them of the heaven's perfect curvature. The sphere is not just geometry, it is a metaphor, a language through which humans have tried to express the deepest truths about existence. When we say that realities can be seen as spheres, we begin to picture the world in a different way. Think of your personal life as a sphere. Everything you know, feel, and experience is contained within it. Your memories stretch across its inner surface, your hopes and fears rest within its layers, and your dreams expand toward its edges. Now imagine another person standing before you. They too have their own sphere of reality. Sometimes your spheres touch. At that point of contact, you share something, a conversation, a friendship, a relationship, a bond of understanding. When the spheres overlap more deeply, you share even more, a common culture, a shared history, or a deep love. Yet, no matter how much two spheres overlap, they are never identical. Each sphere maintains its own center, its own unique wholeness. This way of imagining realities helps us understand that the universe is not a single flat sheet, but rather a vast space filled with countless spheres of experience, each belonging to different beings, different worlds, and perhaps even different dimensions. Nature itself seems to follow this spherical rule. Look at the heavens above. The sun, the moon, the stars, and the planets are all spherical. Gravity itself shapes them this way, pulling matter evenly toward a center until the most stable form appears, a sphere. If you go smaller, you find atoms with their electron clouds forming almost spherical distributions around their nuclei. If you go larger, you find galaxies with halos of stars forming circular and spherical patterns. Even the universe, according to some scientists, may be curved into a larger spherical form. From the smallest to the largest, the sphere seems to be a natural destiny of matter and energy. It is as though existence prefers to arrange itself in spheres, and when we use this shape to represent realities, we are aligning ourselves with this natural law. Imagine now that each reality is a sphere floating in an endless cosmic sea. Some of these spheres are small, representing personal realities, the world you carry within your mind, the life you live each day, your private experiences. Others are vast, representing collective realities, nations, civilizations, cultures, and worlds. Larger still are cosmic realities, the reality of a galaxy, or the reality of the universe itself. These spheres of reality do not exist in isolation. They touch and influence one another. When cultures meet, their spheres overlap, creating shared spaces of art, language, trade, and knowledge. When galaxies collide, their stars and planets mix, creating new structures and new possibilities. Even in the inner life of a human being, different spheres of reality overlap. The sphere of imagination, the sphere of memory, the sphere of reason, the sphere of emotion. Where they meet, new insights and new ways of being are born. The beauty of the spherical model is that it allows for both separation and unity. A flat model of reality would force everything into a single plane, where differences are hard to preserve, but a spherical model allows each reality to have its own center, its own independence, while still being able to touch and share with others. This gives rise to the richness of diversity. Each person's reality sphere is unique, and yet no sphere exists completely cut off. Even the most private reality eventually touches another, whether through language, through action, or simply through the presence of being. The contact between spheres is what makes growth possible. Without it, we would remain locked inside ourselves, never learning, never changing. Let us now take the image further. Imagine that within each sphere there are layers. At the very center is the core of reality, the deepest truth, the purest essence. Around it are layers of experience, perception, and belief. Some of these layers are clear and transparent, allowing light to pass through. Others are thick and cloudy, making it harder to see within. As we move toward the surface of the sphere, we encounter the outer layer, which touches the world beyond. This is where interactions happen, where our personal reality meets the realities of others. The layers within a sphere may shift over time. Memories fade or grow stronger, beliefs change, new experiences settle in, and the entire structure of the sphere reshapes itself. Just as the Earth has layers of core, mantle, and crust, each reality sphere has layers that hold different depths of meaning. Now imagine countless spheres together, forming a grand pattern. Some are clustered closely, forming communities of shared realities. Some drift apart, existing almost in isolation. Some overlap only slightly, sharing just a thin surface of understanding. Others almost merge into one another, creating deeply shared realities like families or cultural traditions. From a higher perspective, the entire universe could be seen as an infinite arrangement of spheres, each one a reality, each one whole, and yet all connected in subtle ways. To make this picture even more vivid, think about dreams. When you dream, you enter another sphere of reality. This dream sphere is connected to your waking reality, but it has its own laws, its own images, and its own logic. Sometimes, the dream sphere overlaps strongly with waking reality, and you wake up with insights or warnings. Other times, the dream sphere seems distant and strange, almost alien, yet it remains part of your larger sphere of being. In this way, realities as spheres help us make sense of the different dimensions of human experience. The idea of realities as spheres also connects to the way science imagines other possible universes. Some physicists believe that our universe may not be the only one. There could be countless others, each with its own laws of physics, each existing as a bubble or sphere in a grand multiverse. Sometimes these spheres might collide, giving rise to strange events or even new universes. Sometimes they remain apart, forever separate. The multiverse, if it exists, would be a vast cosmic foam of reality spheres. Our own universe would be just one among them, and within our universe, countless smaller spheres of personal, cultural, and planetary realities continue to exist, like reflections of the larger truth. On a more personal level, imagining realities as spheres can help us understand relationships. When two people meet, their spheres touch. At first, the contact may be small, just a surface connection, But as they share more, the spheres begin to overlap more deeply. Within that overlap, a new shared reality is born, the reality of friendship, of love, of companionship. This shared sphere does not erase the individuality of each person's sphere, but it creates something new, something greater than the sum of its parts. In the same way, when groups of people come together to form societies, their spheres overlap, creating shared realities of culture, language, and identity. Conflict arises when spheres try to dominate one another, refusing to respect boundaries. Harmony arises when spheres learn to touch without destroying, to overlap without erasing. We can also imagine time itself as a sphere. The past forms the lower hemisphere, the present sits at the equator, and the future rises into the upper hemisphere. All events exist upon the surface, but their positions shift depending on our perspective. In this sense, the sphere of time is always turning, and we are travellers upon its surface. Sometimes we look backward into the past, sometimes forward into the future, but always we're moving along the curve. This model shows us that time is not linear but cyclical, always wrapping around itself, always complete. The sphere also teaches us about balance. Every point upon the surface of a sphere is equally distant from the centre. This means that no point is privileged above another. Applied to realities, this shows us that every perspective, every experience has its own value. No single reality is absolute. Each is simply a different point upon the larger whole. From your point of view, your reality is the centre. From another person's point of view, theirs is the centre. Both are true, and both are part of a greater unity. This teaches humility, reminding us that our reality is not the only one, but one among many. The spherical model also connects to the spiritual traditions of the world. Many mystics describe enlightenment as a state of wholeness, of returning to the centre, of seeing all as one. The sphere represents this wholeness perfectly. When you reach the centre of your sphere, you realise that every point on the surface is equally connected to you. In that moment, separation disappears and unity is revealed. This is why in sacred art the sphere, the circle, and the mandala are so common. They are visual symbols of the inner journey toward completeness. To make this more vivid, let us imagine a traveller who journeys through different spheres of reality. At first, they live within their personal sphere shaped by family, culture, and belief. But as they grow, their sphere touches others. They learn new languages, read new books, travel to new lands. With each contact, their sphere expands, becoming larger, richer, more transparent. At times, their sphere collides with others in conflict, causing cracks and fractures. But from these cracks, new light enters, and the traveller grows. Eventually, they realise that their sphere is not isolated at all, but part of a vast ocean of spheres. They learn to move gracefully among them, touching without clinging, overlapping without destroying. This traveller becomes wise, for they see that the universe itself is a grand dance of spheres, each one a reality, each one a world, each one a reflection of the whole. Even in science, spheres play a role beyond geometry. Consider the electromagnetic fields around the Earth, which form protective spherical layers shielding life from harmful radiation. Consider sound waves that expand outward in spherical patterns. Consider the human eye, itself almost spherical, allowing us to perceive the world. Everywhere we look, spheres appear, reminding us that this is not just metaphor but also physical truth. By thinking of realities as spheres, we gain a tool for compassion. When someone else behaves in a way we do not understand, we can remember that they live within a different sphere of reality. Their experiences, beliefs, and perceptions are shaped by their own centre. Instead of demanding that their sphere match ours, we can learn to touch gently, to explore overlaps, to seek understanding. This does not mean abandoning our own sphere, but recognizing that many spheres exist together, forming the greater whole. The concept of boundaries in physics is one of the most fascinating and at the same time one of the most challenging ideas that human beings have tried to understand. When people hear the word boundary in everyday life, they might think of a fence around a house, a wall that separates two properties, or even a border that marks the end of one country and the beginning of another. These are very physical, visible, and clear boundaries that we can see with our eyes and touch with our hands. In physics, however, the word boundary can mean many things, and very often it does not mean a wall or a fence, but rather an invisible edge, a limit of what can be measured, understood, or even imagined. It is not always something you can point to directly. but it is an idea that tells us where one thing ends and another begins, or where our models of reality stop making sense. Boundaries in physics are not only physical edges but also mathematical ones, logical ones, and even philosophical ones. They describe the lines beyond which equations break down, or where experiments cannot reach, or where human understanding faces a wall of uncertainty. To fully explore what limits or edges mean in theoretical models, we must go on a journey that stretches from the smallest building blocks of matter to the largest structures of the universe, from the tiniest quantum vibrations to the grandest cosmic horizons. Each of these scales reveals different types of boundaries, and each of them forces us to rethink what we mean by reality itself. Let us begin with the simplest example, the boundary of a solid object. If you take a ball in your hand, you can clearly feel its outer surface. That surface is the physical boundary of the ball. It separates what is inside the ball from what is outside the ball, but even here, physics shows us that things are not so simple. At the atomic level, the boundary is not a sharp line. Atoms in the ball are made of nuclei surrounded by clouds of electrons, and those electrons do not stop sharply at some edge, but rather fade gradually in probability. The boundary of the ball, which looks so clear to our eyes, is in reality a fuzzy region where the presence of atoms decreases little by little until there are none. Already in this ordinary object, we see that the concept of a boundary is not absolute, but depends on how closely we look and what level of detail we use. In theoretical models, physicists often draw boundaries to simplify their calculations. For example, when studying the Earth, scientists sometimes treat it as a perfect sphere with a clear surface. They say the radius of the Earth is such and such number of kilometers, and they draw a neat line to represent its surface. In reality, however, the Earth is not perfectly round. It has mountains, valleys, oceans, and even bulges around the equator due to rotation. Yet the simplified model with a sharp spherical boundary is still extremely useful. It allows scientists to make predictions about gravity, motion, and orbits that work very well in practice. This shows us something important. Boundaries in physics are often created by human beings as part of models. They are not always features of the world itself, but tools that allow us to understand and calculate. As we go deeper into physics, the concept of boundaries becomes even stranger. In classical mechanics, which describes how everyday objects move, the boundaries are clear. A car has edges, a planet has a surface, and a pendulum swings between definite points. But when we enter quantum mechanics, the world of the very small, the idea of sharp boundaries almost disappears. In quantum theory, particles do not have precise positions unless measured. They exist as waves of probability spread out over space. This means that a particle like an electron cannot be said to be inside or outside a region in a definite way until you actually observe it. Its boundary is smeared out. The edges of reality at the quantum level are therefore not hard edges but blurred ones, where things fade in and out of possibility. This blurring of boundaries becomes even more dramatic when we think about the boundary between the classical world and the quantum world. We live in a universe where a cat is either alive or dead, where a chair is either here or there. Yet in quantum mechanics, there are situations where systems exist in superpositions, being in two or more states at the same time. The famous thought experiment of Schrödinger's cat illustrates this boundary. In the story, the cat inside the box is both alive and dead until observed. Where exactly does the boundary lie between the quantum rules that allow such strange superpositions and the classical rules that forbid them? Nobody fully knows. This boundary, sometimes called the quantum classical boundary, is one of the deepest mysteries of physics. It shows how the idea of edges is not just about space or surfaces, but about the limits of different sets of laws. Another powerful example of boundaries in theoretical physics comes from relativity. Einstein's theory of general relativity describes how space and time themselves are curved by mass and energy. In this picture, the most dramatic boundaries are those around black holes. A black hole forms when a massive star collapses under its own gravity. It creates a region where gravity is so strong that nothing, not even light, can escape. The boundary of this region is called the event horizon. The event horizon is not a physical surface like the surface of the Earth or the skin of an apple. It is an invisible limit in space-time. If something crosses this limit, it can never come back out. For an outside observer, the horizon is the ultimate boundary between the knowable and the unknowable. Beyond it, events are hidden forever. What is fascinating is that the event horizon is a mathematical boundary created by the geometry of spacetime. You cannot touch it or see it directly, but it shapes the way black holes behave. It is the sharpest edge that physics can imagine, and yet it is not made of matter at all. In fact, modern theories suggest that the event horizon might be a place where quantum effects and gravity meet in mysterious ways, perhaps giving rise to holographic descriptions of reality, where the information about what falls into the black hole is somehow preserved on its surface. Here again, we see how boundaries in physics are not just physical edges but deep conceptual ones that test the very foundations of knowledge. If we look at the universe as a whole, we also encounter cosmic boundaries. Astronomers talk about the observable universe, which is the region of space we can see with telescopes. Light travels at a finite speed, and the universe has a finite age. This means there is a limit to how far we can see. We can only observe as far as light has had time to travel since the beginning of the universe. That distance defines the cosmic horizon. Beyond that horizon, there may be galaxies, stars, and even entire structures, but their light has not yet reached us and may never do so. The observable universe, then, is bounded not by walls or barriers, but by the speed of light and the flow of time. The cosmic horizon is one of the grandest examples of a boundary in theoretical models, showing that even the universe itself appears to have edges to our perception, even if reality continues infinitely beyond them. Boundaries also appear in mathematics, which is the language of physics. When scientists write equations, they often need to set conditions at boundaries. For example, when solving the wave equation, which describes vibrations, sound, or light, the results depend on what happens at the edges of the system. A vibrating string fixed at both ends has standing waves, whose shapes are determined entirely by those boundary conditions. In this way, boundaries are not just limits but essential parts of how physical systems behave. Without them, the models would not be complete. Sometimes, boundaries mark the end of where a theory works. Newton's laws of motion, discovered in the 17th century, worked beautifully for everyday objects and even for planets. But they broke down at very high speeds close to the speed of light and at very small scales where quantum effects dominate. In this sense, Newtonian mechanics had boundaries, limits to its domain of validity. Einstein's relativity and quantum mechanics extended beyond those boundaries. Yet even those newer theories have their own limits. Relativity cannot fully describe quantum particles, and quantum mechanics cannot fully handle gravity. The boundary where the two must meet is still unknown, and finding a unified theory is one of the greatest quests in science. These boundaries are not physical places but conceptual walls, limits of knowledge, where new discoveries are waiting. Another subtle form of boundary arises in thermodynamics, the study of heat and energy. One of the most important ideas in this field is the second law of thermodynamics, which says that entropy or disorder tends to increase. The concept of entropy introduces a boundary between what is reversible and what is irreversible. In principle, the microscopic laws of physics allow processes to run backward. But in practice, we never see a broken egg reassemble itself or smoke return into a match. The arrow of time itself can be thought of as a boundary in physics, a dividing line between the possible and the impossible, between the past and the future. We also find boundaries in quantum field theory, where particles are seen as excitations of underlying fields. The boundaries here are not only spatial but also energetic. For example, the vacuum of space, which seems empty, is actually full of quantum fluctuations. Yet there are limits to how much energy can be localized in a region before it collapses into a black hole. In this way, energy density sets a boundary for physical possibilities. Similarly, in particle accelerators, we discover new particles only up to the limits of the machine's energy. Beyond that boundary, heavier particles may exist, but we cannot reach them yet. In cosmology, boundaries also appear in the very beginning of time. The Big Bang theory describes the universe as expanding from an extremely hot, dense state about 13.8 billion years ago. But the equations of general relativity break down at the singularity of the Big Bang, where density and curvature become infinite. That singularity is another boundary of knowledge. It is not necessarily a real point in time, but rather a place where our current models stop being useful. The true beginning may be described by new physics, perhaps involving quantum gravity. In this way, the boundary of the Big Bang is not just the start of the universe, but also the limit of human understanding. In condensed matter physics, boundaries take on yet another meaning. Materials often have properties that depend strongly on their surfaces or interfaces. For example, in semiconductors, which power all modern electronics, the boundaries between different materials control how electrons flow. In superconductors, surface effects can determine how magnetic fields penetrate. Even in ordinary water, the boundary between liquid and air creates surface tension, which allows insects to walk on water. These examples remind us that boundaries are not just limits but active regions where important phenomena happen. The concept of boundaries even connects physics with philosophy. When we ask what lies beyond the observable universe, or what happened before the Big Bang, or what exists beyond the event horizon of a black hole, we are really asking about the edges of reality itself. Are these edges real, or are they only edges of our perception and knowledge? Do boundaries exist independently of observers, or are they artifacts of how we describe the world? These questions show how boundaries are not only physical but also intellectual, marking the limits of human thought. To make things even more fascinating, some modern theories suggest that boundaries may be illusions. In string theory, for example, particles are described as tiny vibrating strings in higher dimensions. The boundaries of space as we know them may emerge from deeper structures without fixed edges. In holographic theories, the entire universe may be described as information encoded on a boundary surface, suggesting that what we see as three-dimensional space is itself a projection. In such models, boundaries are not obstacles but foundations, the places where the deepest truths are written. In practical terms, boundaries in physics are also crucial in engineering, technology, and daily life. Engineers must respect the limits of materials, which have boundaries of strength and temperature. Astronauts must respect the boundaries of breathable air inside spacecraft. Doctors who use medical imaging rely on mathematical models with boundary conditions to reconstruct pictures of the body. In every case, the concept of limits and edges underlies the way we interact with the world. Ultimately, the idea of boundaries in physics teaches us that reality is not endless chaos, but structured by limits. These limits can be physical, like the edge of a star, mathematical, like the horizon of an equation, experimental, like the reach of a telescope, or conceptual, like the border between known and unknown theories. Yet boundaries are not just endings, they are also beginnings. They mark the points where discovery happens, where we push beyond the familiar into the unexplored. Each boundary, whether in space, time, energy, or knowledge, invites us to ask what lies on the other side. When we think of physics as the grand adventure of understanding the universe, boundaries are the signposts along the way. They tell us how far we have come, how much we know, and also how much remains hidden. They remind us that every wall can be a doorway, every limit a challenge, every edge a horizon. The history of science shows that human beings have again and again stepped beyond boundaries that once seemed absolute. The sky was once thought to be a boundary, but we travelled beyond it into space. The speed of sound was once thought to be a limit, but we broke it. The atom was once thought to be indivisible, but we split it. And yet new boundaries always arise, keeping the journey alive. The concept of boundaries in physics is therefore not something to fear or lament, but something to celebrate. It is the very existence of boundaries that gives shape to knowledge, that defines the playground of discovery. Without boundaries, there would be no questions, and without questions, no science. Each boundary is an invitation to imagine, to calculate, to experiment, and to dream. In the endless quest to understand the universe, the boundaries we encounter are not just edges of reality, but also the edges of possibility, the edges of hope, and the edges of human imagination itself. The mathematical implications of a boundary are far more than a technical matter of drawing a line or setting an edge. They touch on the very heart of how equations describe the world, how models reflect reality, and how imagination stretches itself to contain what lies within limits and what lies beyond. To understand what it means for mathematics to place a boundary is to step into a landscape where numbers, symbols, and shapes are not merely inert objects, but living tools that bend and twist when confronted with the idea of an edge. Boundaries change the nature of calculation, they alter the rhythm of equations, and they challenge the assumptions behind models. They force mathematics to acknowledge that things cannot extend forever without structure. They remind us that every world, whether physical or abstract, needs a frame, and in this frame, every line and curve behaves differently than it would in an infinite field without edges. Imagine first the infinite plane of mathematics, where numbers march endlessly in both directions, where lines can be drawn with no thought of beginning or end, where functions can stretch to infinity without fear of interruption. This is the dream of pure mathematics, a universe of endless continuation. In such a space, a curve can drift forever, an equation can extend without limit, and the imagination never needs to confront the question of where the road stops. But once a boundary is introduced, the story changes. A line that might have extended into infinity now halts. A wave that might have travelled without resistance now bounces back, reflecting against the wall of limitation. The mathematics becomes not simply about the shape itself, but about how the shape interacts with its borders. Take the example of a wave. In mathematics, a wave can be represented as a repeating function, perhaps a sine wave stretching endlessly in both directions. This is a perfect abstraction, a kind of eternal rhythm without pause. But in reality, no wave continues forever. If a wave moves across a string that is fixed at both ends, the wave cannot pass beyond the boundary. Instead, it reflects back, combining with the next wave, creating interference, standing patterns, or harmonics. Suddenly, the mathematics is no longer about the simple equation of a wave, but about the conditions imposed at the edges. These conditions are called boundary conditions, and they change everything. They determine which solutions are possible, which frequencies are allowed, and which patterns can emerge. Without boundaries, the wave equation is infinite possibility. With boundaries, the wave equation becomes a carefully selected family of solutions. This is one of the greatest mathematical implications of boundaries. They turn the infinite into the finite. They take endless possibilities and filter them through the sieve of conditions. Only certain shapes fit. Only certain behaviours are permitted. It is like music played within the walls of an instrument. A guitar string cannot vibrate at just any frequency it chooses. It must vibrate in ways that respect the fixed boundaries at its ends. This creates the notes we hear, the harmonies we recognise, the beauty of sound shaped by mathematics and limits. Without the ends of the string holding it firm, there would be no music at all. The same idea appears in geometry. Consider the difference between drawing a circle on an infinite sheet of paper and drawing it inside a square box. On the infinite sheet, the circle is pure, untouched by any constraint. It sits comfortably, its edges far from any interference. But place the same circle inside a square box and suddenly questions arise. Does the circle fit perfectly inside, touching the sides? Does it overlap, being too large for the box? Does it float inside with empty space around it? Each possibility has mathematical consequences. If the circle touches the edges, then its radius must be exactly half the length of the square's side. If it overlaps, then the boundary of the square cuts through the circle, creating arcs, chords, and intersections that must be calculated. If it floats freely inside, then new relationships are introduced between its position and the edges of the square. In each case, the mathematics is no longer only about the circle itself, but about the dialogue between the circle and its boundary. The idea of a boundary also appears in calculus, that great tool of mathematics used to explore change and accumulation. In calculus, one of the most powerful concepts is the integral, the summing up of tiny parts into a whole. But integrals often depend on limits, the boundaries within which the summing occurs. To integrate a function between two limits is to say, we are not interested in the infinite behaviour of this function across all space, but only in what happens between this starting point and this ending point. The boundary gives meaning to the calculation. Without the boundaries, the integral might stretch into infinity, producing answers that are undefined, endless, or meaningless. With the boundaries, the integral becomes manageable, real, and often deeply connected to physical problems. For example, the distance travelled by an object moving with changing speed is found by integrating its velocity function between the time it starts and the time it stops. The boundaries of time give the mathematics its shape. They make the abstract calculation into a physical truth. Boundaries also alter the very language of mathematics through inequalities. Equations often describe balance, equality, a precise relationship between two sides. But inequalities describe limits, thresholds, and barriers. To say that a number must be less than 5 is to impose a boundary on its possible values. It may wander anywhere it likes in the world of numbers, but it cannot cross that invisible wall at 5. This is not merely a technical detail, it is the essence of control, safety, and design in the real world. Engineers set boundaries for stress on a bridge. The forces must not exceed a certain level. Economists set boundaries for inflation. It must remain within certain percentages. Biologists set boundaries for populations. Too many or too few and the system collapses. Mathematics expresses all these boundaries through inequalities, creating spaces of possibility surrounded by invisible walls. When we enter the realm of theoretical physics, the implications of boundaries in mathematics become even more dramatic. The equations of quantum mechanics, for example, describe particles not as little dots of matter, but as waves of probability. These waves extend across space, suggesting that a particle has a chance of being found in many places at once. But when boundaries are present, such as the walls of a box, the wave is confined. It cannot spread freely but must adjust to the edges. This produces what is known as quantization. Only certain energy levels are possible. Only certain vibrations fit inside the box. A boundary turns continuous freedom into discrete steps. It forces mathematics to reorganize itself, to shift from smooth infinity to carefully spaced rungs of possibility. The world of atoms and molecules, the colors of light, the behavior of electrons, all of these are consequences of boundaries shaping mathematical waves. In relativity, boundaries take on yet another form. Space and time are described as a fabric, curving under the influence of mass and energy. Equations describe how light moves, how planets orbit, how black holes bend reality. But these equations are deeply influenced by the presence of horizons, those strange boundaries in spacetime. A horizon is not a physical wall, yet it acts as one in the mathematics. For example, the event horizon of a black hole is the boundary beyond which nothing can return. To the equations, it is as if space itself ends there. Solutions to Einstein's equations must respect this boundary, and this respect changes their form. The presence of the horizon introduces conditions, restrictions, and new behaviors. The mathematics of relativity is not the same in open space as it is near a horizon. The boundary alters the possible geometries. It defines what information can be seen. It creates the stage for mysteries like Hawking radiation. Even in pure number theory, boundaries appear in subtle ways. The natural numbers stretch endlessly, but when we place boundaries, such as considering only numbers less than 100, or only numbers that are prime within a certain range, patterns reveal themselves more clearly. The boundary forces us to see structure. Infinite series too become manageable only when bounded. An infinite sum often diverges, rushing off into meaninglessness. But give it boundaries, set limits on its terms, and suddenly the sum converges into a neat number. The mathematics transforms under the pressure of edges. Perhaps the most striking way to see the mathematical implications of boundaries is to imagine removing them. Suppose there were no boundaries in geometry. Then every line could run endlessly without meeting another. Every shape could expand forever without limit. But in such a world, measurement would lose meaning. A circle with infinite radius would be indistinguishable from a line. A polygon with infinite sides would dissolve into nothing. Boundaries are what give mathematics its precision, its ability to compare one thing to another. Without them, the world of numbers would blur into a haze. The presence of boundaries also introduces the idea of symmetry and breaking symmetry. When a mathematical object is placed in an unbounded space, it may enjoy perfect symmetry. A wave in infinite space looks the same in every direction. A function stretching without end respects the same rules everywhere. But introduce a boundary, and symmetry shatters. The wave may now look different near the edge. The function may behave differently at the limit. This breaking of symmetry is not a flaw. It is a source of richness. It is what gives rise to structures, patterns, and forms that could never exist in perfect infinity. The finite, the bounded, the contained, these are the ingredients of complexity. Think of fractals, those intricate shapes that repeat endlessly on smaller and smaller scales. A fractal pattern can in theory extend forever, its complexity unbounded. But when we render fractals on a screen or paper, we must introduce boundaries. We must decide how many iterations to allow, where to stop the infinite process. These boundaries do not destroy the fractal, they make it visible. They allow the infinite to become tangible. The mathematics of the fractal is altered by the stopping point, but it is also brought into the human world by that very act of limitation. One of the deepest implications of boundaries in mathematics is that they often transform unsolvable problems into solvable ones. An equation that seems hopelessly complicated in the infinite case may become simple once boundaries are applied. For instance, the heat equation describes how temperature spreads across a medium. On an infinite plane, solving the equation is challenging, requiring advanced tools. But on a finite rod with fixed temperatures at the ends, the problem becomes solvable with neat solutions in the form of sine waves. The boundaries filter out the noise. They guide the mathematics toward clarity. Boundaries also give rise to entirely new fields of mathematics. Topology, for example, studies the properties of shapes under continuous deformation. A donut and a coffee cup are the same in topology because they each have one hole. But once boundaries are introduced, the classification changes. A surface with edges is topologically different from one without. The very identity of a shape is altered by whether or not it has boundaries. The mathematics of topology cannot ignore edges. They are part of the fundamental essence of form. In computer science, mathematics is always bounded by necessity. A computer cannot store infinite numbers. It cannot calculate with endless precision. Every algorithm works within limits of memory, time, and processing power. These boundaries shape the mathematics of computation. Numbers are rounded, functions are truncated, infinity is replaced by large but finite approximations. The very logic of algorithms is built around conditions, loops that stop at boundaries, decisions that hinge on whether a value exceeds a threshold. In this way, boundaries transform the infinite purity of mathematics into the finite practicality of machines. Boundaries in mathematics are not just about restrictions, they're also about creativity. By setting limits, they invite exploration of what is possible within those limits. Artists know this truth well. A blank canvas without edges is overwhelming, but a canvas with fixed dimensions sparks imagination. In the same way, mathematicians thrive within boundaries. They discover patterns in prime numbers less than 1,000,000. They explore the geometry of shapes that fit inside a cube. They test algorithms that run within a given number of steps. Boundaries do not silence mathematics, they give it voice. This interplay of freedom and limitation is perhaps the most fascinating implication of boundaries. Mathematics without boundaries is an ocean without shore, vast but ungraspable. Mathematics with boundaries is a sea with coasts, where waves crash, where patterns form, where life can take hold. It is at the edges, where the infinite meets the finite, that the most interesting things happen. Equations become stories, models become worlds, boundaries give mathematics its drama, its tension, its meaning. When we think of models, the role of boundaries becomes even more dramatic. A mathematical model is a representation of reality, a simplification that captures the essence of a system. But every model exists within boundaries. A climate model, for example, cannot calculate every molecule of air and water across the Earth. Instead, it divides the planet into regions, grids bounded by size and scale. Within each grid, averages are taken, equations are applied, predictions are made. The boundaries of the grid shape the behavior of the model. Too coarse a grid, and the model misses important details. Too fine a grid, and the model becomes impossible to compute. The mathematics bends to the edges of the chosen frame. Economic models, too, are built on boundaries. They consider markets within certain countries, time frames or conditions. Remove the boundaries, and the model collapses under the weight of infinite variables. Apply boundaries carefully, and the model becomes a useful tool for prediction. Biological models, engineering models, social models, all depend on where the edges are drawn. The boundaries are not accidental, they are fundamental. They determine what the model can say and what it cannot. They shape the equations, filter the possibilities, and decide the meaning of the results. Even in the realm of imagination, boundaries play their role. Think of mathematics as a game. A game without rules is chaos, but a game with rules becomes meaningful. The rules are the boundaries, the conditions that define what moves are allowed, what goals can be pursued, what strategies can succeed. In mathematics, boundaries are the rules of the game. They tell equations where they may go and where they must stop. They give structure to play, turning abstract numbers into elegant dances. The implications of boundaries also reveal something profound about the relationship between mathematics and reality. In the mind, mathematics can be infinite, pure, unbounded. But in the physical world, everything has edges. Every object has size. Every process has duration. Every system has limits. To apply mathematics to reality, boundaries must be acknowledged. This is why boundary conditions are not optional details, but essential features of applied mathematics. They tie the abstract to the real. They remind us that while imagination can soar into infinity, the universe itself is framed by edges. The impact on the nature of space and time when we begin to think about boundaries is something that carries with it not just a touch of curiosity, but also a sense of mystery that stretches the imagination. The universe is usually imagined as endless, an open stage without walls or fences, a place where galaxies drift and stars are born and die in what feels like an eternal dance. Yet when the idea of a boundary is brought in, even as a thought experiment, the whole picture of space and time begins to bend, twist, and take on forms that challenge what we believe we know. Boundaries are more than just edges, more than just endings. They are places where rules can change, where continuity can be interrupted, where one set of conditions may give way to another. To imagine boundaries in the framework of space-time is to imagine how the deepest structure of the cosmos could be reshaped, and with that comes a cascade of new ways of thinking about reality itself. In the simplest sense, a boundary is an edge, or a limit. If you stand at the edge of a cliff, you know that the ground stops there. If you place water in a glass, the boundary is the rim of the container that holds it in. But space and time are not cliffs or glasses of water, and so the thought of them having a boundary is not straightforward. Space feels like it goes on forever, stretching in every direction without an end. Time feels like it ticks endlessly, one moment following another with no natural stopping point. If these were to have edges, what would those edges be like? Would there be a wall in the sky, invisible but solid, marking the end of the universe? Would time simply stop at some moment, as if the final second could arrive and then nothing more could come after it? Or would the boundary be less like a wall and more like a transformation, where one kind of reality turns into something entirely different? When thinkers, scientists, and dreamers play with these questions, they often compare the universe to shapes that we can imagine more easily. One of the most common shapes is a sphere. A sphere, like a ball or a planet, has a surface, and that surface can be travelled endlessly without ever encountering an edge. If you walk around the Earth, for example, you can keep going forever, circling and circling without falling off. The Earth's surface is finite in size, but it has no boundary. This image helps explain how the universe might work. Space could be curved back on itself, large but without a hard edge, so that travelling far enough might one day bring you back to where you began. In such a case, the boundary is not a sharp end but a continuous loop. And yet, there are other ideas too. Ideas that imagine real edges, real transitions, real shifts from one side of existence to another. If space had a boundary, that boundary could become a powerful place where the rules of physics shift. Within the universe, we are guided by laws such as gravity, the speed of light, the structure of atoms, and the stretching of space-time. At a boundary, those laws might break down or transform into something else. It could be that light cannot pass through a boundary, bouncing back like sound echoes off a wall, or it might be that light passes through, but what exists beyond the boundary is something unrecognizable to us, a region where time flows differently or space behaves in ways we cannot measure. If such a boundary existed, it would not just be a limit to where we could travel, it would be a stage on which the deepest secrets of the cosmos are written. This reshaping of space-time through the idea of boundaries becomes even more fascinating when we think about how time itself could be altered. Time is usually felt as a river, flowing from past to present to future. But if time had boundaries, what would that mean? Could there have been a beginning that truly was a boundary, a moment where time itself sprang from nothingness? Could there be an ending boundary, where time collapses into silence and no further moments are possible? The Big Bang is often thought of as a beginning boundary, the point where space and time emerge together, and the potential big crunch or heat death of the universe might be imagined as future boundaries. But boundaries in time need not only be beginnings and endings, they could also be points within the flow where time behaves differently. Imagine reaching a moment where time slows to a stop, like a frozen pond, while everything else continues. To step across such a boundary would not be to move into the next moment, but to leave the river of time altogether, entering a stillness beyond experience. The mathematical models that scientists use to explore the universe often play with these ideas. Equations describing curved spacetime show how mass and energy can bend the geometry of the cosmos. Within these equations, boundaries can emerge as special conditions, places where the values break down or take on new forms. For instance, the event horizon of a black hole is often described as a kind of boundary, though not a physical wall. It is a place where space-time bends so extremely that not even light can escape. From the inside, time and space seem to change roles, and the normal order of things falls apart. Here, the idea of a boundary reshapes our understanding of both space and time, turning them into something unfamiliar and strange. Black holes are, in many ways, natural examples of how boundaries might function in the universe. The edge of a black hole is a boundary between the visible world and the hidden core. Outside you can see stars, planets, and light, but once something crosses the horizon, it is cut off from the rest of the universe. This is not just a matter of being hidden. The very fabric of space and time inside the black hole is not the same as outside. For an outside observer, objects falling in seem to freeze at the boundary, never quite crossing. For the object itself, however, it plunges through and experiences the inside as a continuation of space and time. This shows how boundaries in space-time are not just lines drawn in the sky, but living conditions that can make the very flow of time depend on where you stand. If we stretch the imagination further, we might picture boundaries not just as the edges of black holes, but as cosmic divisions between entire regions of reality. Some theories suggest that our universe might be one bubble among countless others, each bubble surrounded by a boundary that separates it from the next. These boundaries could be like the thin membranes between soap bubbles, fragile yet absolute, marking off one cosmos from another. If that were true, then boundaries would not just reshape space and time within a single universe, but they would also define the relationship between all possible universes, a grand architecture of existence where every bubble has its own space-time and its own destiny. Boundaries also carry emotional weight, because they are tied to our own human sense of edges and endings. We live our lives bounded by time, knowing that every day has a beginning and an end, every life has its start and finish. To think of space and time themselves as bounded is to mirror something deeply human onto the cosmos, to see the grand universe reflect the same patterns that shape our own lives. But while our own boundaries may feel like closures, in the cosmos they may also be doorways. What seems like an end could instead be a threshold to something beyond. A boundary in space-time could be the place where one form of reality ends and another begins, not a wall, but a gate. One could imagine standing at such a boundary. Imagine walking across the universe, billions of light years from home, and finding the very edge of space. What would it look like? Would there be a surface glowing with strange energy, a curtain of light marking the end of what we know? Would it be invisible, detectable only by the sudden stopping of your journey, an invisible wall that no step could cross? Or would it be more subtle, a fading away of stars and galaxies until nothing remains but silence and darkness, leaving you unsure if you're at an end or simply lost in an emptiness without measure? And if you touched it, if you pressed your hand or your ship against it, would you feel resistance, or would you pass through and find yourself in another form of existence altogether? In science fiction and myth alike, boundaries of space and time have been imagined as thresholds into the unknown. The edge of the universe is often drawn as a place where travellers might slip into other dimensions, where time loops back upon itself, or where entirely new laws of physics take over. These stories, though not scientific, capture the emotional intensity of the idea. Boundaries are places of danger, of wonder, of transformation. And this is not far from how scientists themselves sometimes think, for in the hardest equations of cosmology and quantum theory, boundaries appear as mysteries waiting to be solved, signals of where our understanding runs thin. The mathematics of relativity suggest that the shape of the universe could depend on whether it is finite or infinite, bounded or unbounded. A universe with boundaries could be like a drum, its edges defining vibrations that ripple through space-time. Waves of gravity, energy, and even particles might bounce off boundaries, creating echoes that shape the structure of galaxies and stars. If boundaries exist, they may not just be passive endings, but active shapers of the cosmos, guiding the music of creation like the edges of an instrument. Quantum mechanics, too, has its own way of seeing boundaries. In the strange world of the very small, particles are often described in terms of probability waves, spread out and uncertain until measured. Boundaries in this quantum world define where a particle can exist and where it cannot. Electrons in atoms, for example, are bound by invisible edges that shape their orbitals. They cannot wander freely. They are confined to regions where the equations allow them to be. If this principle were extended to the entire cosmos, then spacetime itself might be bound by a greater set of quantum boundaries, invisible yet absolute, deciding what is possible and what is forbidden. The impact of thinking in this way reshapes more than just physics. It reshapes philosophy. If space and time are bounded, then reality itself is not an infinite expanse, but a designed structure with edges, shapes, and contours. This would mean that existence is not random chaos, but something with form. To know the boundaries would be to know the true size and nature of reality, perhaps even its purpose. And yet, if boundaries do not exist, then the universe may be endless, without measure, without edges, flowing outward into infinity. Each possibility carries its own kind of wonder, its own kind of awe, reshaping how we understand not just science but ourselves. The idea of boundaries in space-time also touches upon the deepest mysteries of the human spirit, the longing to know what lies beyond. From the earliest days, humans have walked to the edges of their lands, sailed to the horizons of their seas, and looked to the skies for signs of what lies past the stars. Each boundary encountered has led to discovery. Each edge has been a doorway to something greater. And so, when we think of the universe itself, the thought of a boundary is not just an abstract idea, but a call to explore, to wonder, to imagine stepping past the greatest edge of all and seeing what lies beyond space and time itself. Introducing the idea of a limit in string theory is like trying to imagine how something that is so small and so mysterious could still be governed by edges or boundaries. When physicists speak of strings, they are not describing ordinary pieces of thread or rope, but instead the tiniest possible objects in the universe, so tiny that no microscope could ever see them directly. These strings are imagined to vibrate and move, and their vibrations give rise to all the particles and forces we know in physics. A photon, which carries light, or an electron, which makes up part of atoms, or even the particles that hold atomic nuclei together, are not thought of as separate basic objects in string theory, but as different musical notes played by the same kind of fundamental string. The universe, in this way of thinking, is a grand cosmic symphony, and every piece of matter and energy is just a vibration of strings. But even this picture, as magical as it sounds, must deal with the question of limits. In everyday life, limits and boundaries are easy to imagine. A table has edges, a football field has lines marking where it ends, a city has borders that separate it from surrounding towns. But when the subject turns to strings and spheres in physics, the idea of a boundary becomes far more subtle. Strings are thought to be unimaginably small, smaller than anything else that has ever been measured, so the very act of asking whether they have ends or whether they stretch on without limit becomes a puzzle. Are they like open strings with two loose ends? Are they like closed loops, tiny circles that wrap back on themselves? Each possibility has enormous meaning for how the universe itself works. When we talk about spheres in physics, we also face similar puzzles. A sphere seems simple to the eye. A ball has a clear surface, and the surface is its boundary. It separates what is inside from what is outside. Yet when physicists imagine spheres in the abstract sense, as in higher dimensional spaces or within string theory, those boundaries are not always so simple. Sometimes the edge is not really an edge, but instead something that folds back on itself. In higher dimensions, the surface of a sphere might behave in ways that no ordinary ball ever could. The idea of a boundary is stretched and twisted, and what looks like an end from one perspective may turn out to be a continuous loop from another perspective. Limits in string theory are not only about physical edges, but also about what can be known, measured, or calculated. In mathematics, the word limit carries a very precise meaning. It refers to what happens as you get closer and closer to something, even if you never fully reach it. Imagine walking halfway to a wall, then halfway again, then halfway again. You may never actually touch the wall in this thought experiment, but you will keep approaching it, closer and closer. In mathematics, this process is captured by the idea of a limit. In string theory, limits often appear when equations are pushed to extreme scales, whether extremely small distances, or extremely high energies, or extremely large curvatures of space and time. At these extremes, our usual understanding begins to break down, and the boundaries of knowledge become visible. One of the biggest puzzles of modern physics is how to bring together the rules of general relativity, which describe the fabric of space and time on large scales like stars, galaxies, and the universe as a whole, with the rules of quantum mechanics, which describe the behavior of particles on the smaller scales. Each system of rules works beautifully in its own domain, but when they collide, contradictions appear. String theory was proposed as a way to overcome these contradictions by offering a new picture where particles are not points but strings. But even here, the question of limits arises. Where do the strings stop? Do they have an ultimate smallest size? Can they be infinitely stretched? Is there a limit to how much they can vibrate, or a boundary beyond which the equations cannot describe reality? To make sense of this, physicists sometimes imagine thought experiments. Suppose there is a tiny string vibrating in the vacuum of space. If you try to zoom in closer and closer, ordinary physics would suggest you could keep magnifying forever. But in string theory, at some point, further magnification no longer makes sense. The string has a characteristic length, often called the Planck length, which is unimaginably small, about 1 divided by a number with 35 zeros after it meters. At this scale, the very concept of space itself may no longer behave as we expect. It may become foamy, uncertain, or even dissolve into pure mathematical relations. The limit is not only a physical boundary, but a limit of language and imagination. Another way to think about limits in string theory is through dualities. A duality is when two very different-looking theories turn out to describe the same thing. For instance, a theory that describes small strings might turn out to be exactly the same as a theory that describes large strings, just from a different point of view. This means that what looks like a boundary in one perspective may vanish in another. The limit between small and large loses its absolute meaning. Just as a map can make two distant places look close depending on how it is drawn, so too can string theory reveal that boundaries depend on perspective. When spheres are brought into the picture, the story becomes even richer. Imagine space not as a flat, endless sheet, but as a curved sphere. On Earth, if you keep walking in one direction, you eventually come back to where you started. There is no edge, no cliff where the world stops. The boundary is an illusion created by expecting flatness. In string theory, higher dimensional spheres can behave in similar ways. What looks like an end might be a loop. What appears to be a limit could be a doorway into another form of continuity. For example, certain spheres in string theory are thought to wrap around dimensions that are curled up so tightly we cannot see them, like tiny secret chambers hidden within every point of space. These compactified dimensions are bounded, yet they connect back into themselves. The boundaries are real, but they are not endings. They are more like pathways. Physicists also use the word limit when they test the strength of their theories. A good theory must reduce to older, proven theories in the right limits. For example, string theory, in the limit where strings become very small compared to the scales being studied, should behave like ordinary particle physics, because in that limit the strings are too tiny to notice and they look like point particles. In another limit, where energy and curvature are very high, the theory should reproduce aspects of general relativity. This is how physicists check whether a theory is consistent. They push it to the boundaries of its domain and see whether it behaves as it should. These limits act like tests of honesty, forcing the theory to show its compatibility with reality. The very concept of a boundary is also central when string theory deals with black holes. A black hole has what is called an event horizon, which is a kind of ultimate boundary. It marks the limit beyond which no information can escape, not even light. In ordinary relativity, this horizon is smooth and featureless. But in string theory, the horizon may be composed of complicated states of strings and branes. The edge is not just a void, but a rich structure of vibrating possibilities. Some physicists even argue that the information paradox of black holes, the puzzle of what happens to information when matter falls in, could be solved by understanding how string theory handles boundaries. The horizon, once thought of as an absolute edge, may instead be a fuzzy or holographic boundary, where information is preserved in new and subtle ways. Boundaries also appear in the study of branes, which are higher dimensional objects that string theory predicts. A brane can be thought of as a membrane, a surface that may have any number of dimensions. Open strings can have their ends attached to branes, while closed strings float freely. In this picture, the universe we see may itself be a brane, a vast surface in higher dimensional space, and the boundaries of strings are literally tied to it. The limits of our perception, then, might be shaped by the boundaries of strings interacting with branes. Our universe could be a boundary inside an even greater cosmos, the way the surface of a bubble is just one boundary in a froth of bubbles. Even the mathematics of string theory is filled with boundaries and limits. Equations that describe the energy of strings often run into infinities, and physicists must carefully handle these by taking limits that cancel out meaningless results. Whole areas of research are devoted to understanding how boundaries in mathematics reflect boundaries in physics. The concept of renormalization, for example, is about taming infinities by redefining limits. Without careful attention to boundaries, the entire structure of the theory would collapse into nonsense. At a deeper philosophical level, the idea of limits in string theory mirrors the limits of human understanding. Whenever we ask questions about what lies beyond space, or before time began, or beneath the smallest particle, we are pressing against boundaries of thought. Some physicists believe string theory points to answers beyond those boundaries, while others argue that it reveals the very limits of what science can ever explain. Just as a map of the Earth cannot tell you what lies beyond Earth's surface, a theory may not be able to tell you what lies beyond space and time themselves. The boundary in this sense is not physical, but conceptual. Yet there is also beauty in this. Boundaries give shape to meaning. Without an edge, we would not know what is inside or outside. Without limits, motion and change would lose their sense. A string vibrating without any boundary at all would not give rise to distinct notes. It is precisely the constraints, the limits, and the edges that allow the universe to sing its varied song. The same is true for spheres. Their surfaces, their boundaries, make them what they are. To understand boundaries in string theory, then, is to understand how structure, meaning, and possibility arise out of the fabric of existence. When Albert Einstein first described general relativity in the year 1915, he too was grappling with limits, the limit of Newtonian gravity and the boundary of classical physics. When quantum mechanics was developed in the 1920s, physicists again encountered boundaries, the limit of certainty, and the boundary where particles could no longer be described as little marbles but only as waves of probability. Now, with string theory, we find ourselves once more at the edge, staring into boundaries that may reveal deeper truths. The idea of a limit is not just a mathematical tool but the very outline of the human quest to understand reality. The multiverse is an idea that tries to explain something much bigger than what we usually think of when we say the universe. It is a hypothesis suggesting that our universe might not be the only one, but instead just one bubble among countless others floating in an unimaginably vast reality. When scientists and thinkers talk about the multiverse, they mean the complete collection of all possible universes put together. This collection would include everything, every bit of space, every tick of time, every particle of matter, every burst of energy, every piece of information, and even the very physical laws and constants that describe how things work. Within this grand multiverse, each universe can be thought of as a separate chapter in an endless book of reality. People call these other universes by many different names: parallel universes, alternate universes, multiple universes, flat universes, parent universes, child universes, plane universes, many worlds, or simply other universes. One common picture is to imagine the multiverse as a patchwork quilt, with each patch being a separate universe, stitched together yet following the same general physical rules. The idea that there might be more than one universe is not new. It has appeared many times throughout history, changing and evolving as human understanding grew. Philosophers, scientists, and dreamers have all debated it, each from their own perspective. In modern times, cosmologists and physicists have studied it seriously, but some of them say it is more philosophy than science, because it cannot be directly tested or disproven. A key part of science is testability. An idea must be able to be proven wrong if it is false. Critics argue that the multiverse concept does not meet this standard, and therefore belongs more to the world of imagination and metaphysics than to the laboratory. Still, some researchers have tried to look for signs of other universes in the data, though so far no clear and undeniable evidence has been found. The debate continues, with strong believers and strong skeptics arguing passionately about what the multiverse means. Different scientists have tried to organize the concept in their own ways. the Swedish-American physicist Max Tegmark proposed a 4-level system. His level 1 describes parts of space beyond what we can see, like an extension of our own universe. Level 2 includes universes with completely different physical constants, where the very rules of nature might change. Level 3 connects to the many worlds interpretation of quantum mechanics, where every possible outcome of an event actually occurs in a separate branch of reality. Level 4 is the most ambitious, describing an ultimate ensemble of all mathematically possible universes. The American physicist Brian Greene expanded this further, suggesting 9 possible types of multiverses: quilted, inflationary, brane, cyclic, landscape, quantum, holographic, simulated, and ultimate. Each of these ideas digs deeper into different aspects of space, mathematics, and physical laws, painting a picture of reality that is far larger and more complex than the one we know. Other theories add even more possibilities, such as twin-world models, cyclic universes that repeat forever, M-theory with its extra dimensions, or black hole cosmology, which imagines new universes being born inside black holes. One reason the multiverse idea remains powerful is because of something called the anthropic principle. This principle tries to explain why our universe seems so perfectly balanced for life. The physical constants of nature, the strength of gravity, the charge of the electron, the speed of light, and so on, are so finely tuned that if they were even slightly different, stars, planets, and living beings like us might never have formed. The weak anthropic principle suggests that we live in one of the rare universes where conditions just happen to allow life, while countless other universes exist where conditions do not. Supporters argue that this explanation makes more sense than believing ours is the only universe. Debates also rise around Occam's razor, a philosophical idea that prefers the simplest explanation. Some argue that one single universe is simpler, while others like Max Tegmark argue that the multiverse is actually the simpler idea because it avoids the problem of explaining why our universe looks so specially fine-tuned. These discussions even touch on quantum mechanics, with its many worlds interpretation, and modal realism, the belief that all possible worlds exist just as fully as ours. The seeds of the multiverse idea go back thousands of years. Some say the pre-Socratic philosopher Anaximander, in the 6th century before the Common Era, may have suggested the idea of infinite worlds, though it is debated whether he meant them to exist all at once or one after another. The first clear advocates of innumerable worlds were the ancient Greek atomists, beginning with Leucippus and his student Democritus in the 5th century before the Common Era. Later, Epicurus, who lived from the year 341 to 270 before the Common Era, and the Roman poet and philosopher Lucretius in the 1st century before the Common Era, also described worlds without number. The philosopher Chrysippus in the 3rd century before the Common Era added his own view, suggesting that the cosmos continually perished and was reborn, which could be seen as a version of multiple universes across time. By the Middle Ages, the idea had become more clearly defined, and in the Renaissance, the Italian thinker Giordano Bruno, who lived from the year 1548 to 1600, boldly spoke of infinite worlds stretching into the vastness of space. The word multiverse itself was first used in the year 1895 by the American philosopher and psychologist William James, though he meant it in a different sense than scientists do today. Around the same year, the concept appeared in modern scientific discussions during a debate between Ludwig Boltzmann and Ernst Zermelo. Later, in Dublin in the year 1952, the physicist Erwin Schrödinger gave a lecture where he half-jokingly admitted that what he was about to say might sound crazy. He explained that his equations did not just describe one history of events, but many at once, and that all of them actually happened together. This strange idea is called superposition, a cornerstone of quantum mechanics. In the 1990s, the multiverse became more widely talked about, helped by works of fiction that captured the imagination of the public. Scientific journals also began to publish more articles about it. Then, in the early 21st century, around the year 2010, researchers like Stephen Feeney studied data from the Wilkinson Microwave Anisotropy Probe, known as WMAP, to see if there was evidence that our universe might have collided with others in the distant past. At first, they thought they might have found hints of such collisions. However, when the data was studied more carefully, especially using the Planck satellite, which had 3 times the resolution of WMAP, the evidence did not hold up. No clear signs of bubble universe collisions were found, nor was there evidence that other universes were pulling on ours through gravity. In the year 2015, more speculation arose when astrophysicist Rangaramchari analysed the cosmic radiation spectrum and discovered a signal much brighter than expected. This signal was about 4,500 times stronger than what should have existed based on the known number of protons and electrons in the early universe. He suggested that maybe this was evidence of a parallel universe spilling particles into our own during the era of recombination, when the first atoms formed after the Big Bang. If that had happened, extra protons and electrons would have created more atoms, releasing more photons and leaving behind a stronger signature. But he also admitted that there was about a 30% chance that the signal was just noise. Whether it was evidence of another universe or just a mistaken measurement remains unsettled. The unusual cosmic signature that the researcher Chari detected might not be something extraordinary at all. It could simply be light streaming in from galaxies that lie very far away, or it might even be caused by swirling clouds of cosmic dust that hang around the edges of our own Milky Way galaxy. Back in the year 2003, the well-known cosmologist and science writer Paul Davies published an opinion article in the New York Times called A Brief History of the Multiverse. In this piece, he put forward several reasons why he believed that the idea of the multiverse should not really be considered scientific. Several years later, in August of the year 2011, another respected thinker, George Ellis, offered his own sharp criticism. Ellis explained that the concept of the multiverse is not a scientific theory in the usual sense. He admitted that many researchers imagine the multiverse to exist far beyond what we can see, past the outer limit of our observable universe, also known as the cosmological horizon. But Ellis stressed that the supposed multiverse is thought to lie so impossibly far away that no evidence is likely ever to be gathered. Some scientists are comfortable with this, arguing that testability is not the most important issue. But Ellis firmly disagrees. For him, science without observational testing is no science at all. He insisted that building explanations without the possibility of proof or disproof reduces the idea of the multiverse to something closer to philosophy or metaphysics, not true physics. Philosopher Philip Goff added another layer to this debate. He argued that using the multiverse to explain why our universe appears so finely tuned for life is logically flawed. He compared it to the inverse gambler's fallacy, a mistaken reasoning where people assume that because something rare happened, there must have been many chances for it to occur. Ellis, together with Stuger and Kircher, pointed out an important issue. If a multiverse truly exists in its purest form, then all the universes within it would be entirely separate and disconnected. Nothing that happens in one universe would ever affect anything in another. With no cause and effect ties between them, Ellis argued, such universes would forever remain beyond the reach of scientific study. In May of the year 2020, astrophysicist Ethan Siegel wrote a blog post for Forbes. In it, he argued that, based on the evidence we have today, parallel universes must remain in the realm of science fiction dreams rather than established scientific reality. Other critics have also spoken strongly. John Horgan, a longtime contributor to Scientific American, dismissed the multiverse idea, calling it bad for science, because it pulls physics away from testable reality and into endless speculation. On the other hand, not everyone rejects the multiverse so harshly. Some cosmologists, like Max Tegmark and Brian Greene, have worked hard to bring order to the wild variety of multiverse ideas. They created ways to classify and sort them into different categories. Tegmark in particular laid out a kind of map, or taxonomy, of universes that go beyond the one we can observe. His scheme has 4 levels, each building on and including the one before it, like layers of imagination stacked on top of each other. One of the predictions of the cosmic inflation theory is the idea of an infinite ergodic universe. Because it stretches on without end, such a universe would contain an unlimited number of regions called Hubble volumes. Each of these regions would obey the same physical laws and constants as ours, but the specific arrangement of matter, stars, galaxies, dust and planets would differ. Still, because there are infinitely many of these volumes, there must eventually be some that look almost identical to ours, and even some that are completely identical. Tegmark even calculated that an identical Hubble volume to ours should exist, unimaginably far away, at a distance of about 10 raised to the power of 115 meters. That is a number so vast it defies imagination. The logic of infinity leads to a curious conclusion. If space is truly endless, then there would be an infinite number of copies of our universe, repeating every detail, including you, me, and everything around us. According to the cosmological principle, our own Hubble volume is not special or unique, which means infinite repetition is unavoidable. Another version of inflation theory, called eternal inflation, suggests that space will keep expanding forever. But within this expansion, certain regions stop stretching and form separate bubbles, like pockets of air trapped in a loaf of bread that is rising in the oven. Each bubble can be thought of as its own universe, a kind of embryonic level 1 multiverse. Different bubbles might have different physical laws or constants, depending on how they formed. This is known as level 2 of Tegmark's classification, and it even includes earlier theories like John Archibald Wheeler's oscillating universe idea and Lee Smolin's proposal of fecund universes that reproduce through black holes. The next level of the multiverse comes from quantum mechanics, specifically Hugh Everett III's many worlds interpretation. Quantum mechanics tells us that at the smallest scales, the outcomes of events are not fixed but spread across a range of possibilities. Everett's bold idea was that instead of just one outcome happening, all possible outcomes occur, but in different worlds. For example, if someone rolls a 6-sided die, then 6 different universes exist, one where it landed on 1, another where it landed on 2, and so on. Similarly, in the famous thought experiment with Schrödinger's cat, there would be one world where the cat lives and another where the cat dies, both equally real. Tegmark explained that a level 3 multiverse does not actually add more possibilities than levels 1 or 2. All the worlds created by these quantum splits could already exist as regions in an infinite level 1 multiverse. The only difference, he said, is location. In level 1, your lookalike lives somewhere far away in regular 3-dimensional space. In level 3, your twin lives on another quantum branch within an infinite-dimensional mathematical space called Hilbert space. Some researchers, like Yasunori Nomura, Raphael Bousso, and Leonard Susskind, even argue that the different levels of the multiverse are really the same thing viewed in different ways. They call this idea multiverse equals quantum many worlds. According to this way of thinking, the global spacetime of eternal inflation is unnecessary. Nomura went further, suggesting that this quantum multiverse is unchanging and that what we experience as the flow of time might be nothing more than an illusion. Others, like physicist H. Dieter Zeh, expanded Everett's vision in different directions, proposing the many minds interpretation, where it is not the universe that splits, but rather the consciousness of observers. The brane multiverse idea suggests that our entire universe is not floating in empty space by itself, but instead lies on a vast sheet, known as a brane. This brane does not exist alone. It drifts within a larger and higher dimensional space called the bulk. Inside this mysterious bulk there are countless other branes, each carrying its own universe with its own rules, structures, and history. These branes do not simply remain still. They move, shift, and drift, sometimes getting close to one another. When two branes collide, the force of the impact unleashes unimaginable energy, so powerful that it can spark the birth of a new universe through what we call a Big Bang. According to this idea, such collisions are not one-time events but happen again and again. Every few trillion years, branes are pulled back toward one another, perhaps by gravity or perhaps by a force beyond our current understanding. When they crash together, the old universe is destroyed, and a new one is born in its place. This cycle of destruction and rebirth paints a picture of an endless rhythm of creation, often referred to as a cyclic multiverse. The idea belongs under the larger family of string theory since it requires extra dimensions of space beyond the familiar ones we can see. In this cyclic version of the multiverse, countless branes have collided across eternity, each time producing a Big Bang. After such an event, universes expand, pass through their lifetimes, and eventually are drawn back together to collide again. Each collision wipes away what came before and creates something entirely fresh, giving rise to a grand story of renewal written across cosmic time. Another vision of the multiverse is known as the landscape multiverse. This relies on string theory's strange and beautiful mathematical shapes called Calabi-Yau spaces. These shapes represent the hidden extra dimensions of the universe. Quantum fluctuations, tiny, restless movements in the energy of space, can cause the geometry of these shapes to drop into lower energy states. Each drop gives rise to a small pocket of reality with its own distinct physical laws, unlike the laws of the space around it. These pockets are like separate little universes within a greater multiverse. The quantum multiverse, on the other hand, comes from the puzzling world of quantum mechanics. In this picture, whenever an event could unfold in more than one way, the universe splits into new versions, with each possible outcome happening in its own separate branch of reality. This means that every choice, every chance, and every roll of the cosmic dice could create another universe. This is similar to the many worlds interpretation of quantum physics, where all possibilities are realized, but each in its own universe. Another fascinating vision is the holographic multiverse. This stems from the idea that all the information within a volume of space, everything inside a universe, can be encoded on its boundary or surface, much like a hologram stores a three-dimensional image on a flat two-dimensional sheet. If this holographic principle is true, then universes themselves could be described by information stored on higher dimensional surfaces, suggesting realities beyond our own. There is also the simulated multiverse, which imagines that entire universes could exist within the minds, or machines, of advanced civilizations. In this scenario, universes might be generated by extraordinarily powerful computers that can simulate not just stars and planets, but the very laws of physics themselves. Astronomer Avi Loeb has even suggested that such universes might not just be simulations, but could actually be created in laboratories by civilizations far ahead of us, who may already possess a complete theory of everything. Related to this is the brain in a vat style of hypothesis, where the universe we experience is not real at all but an illusion, either a low-resource simulation or a perception crafted within some artificial system. The ultimate multiverse theory goes further than all the rest. It proposes that every mathematically possible universe exists somewhere. In this boundless collection, there are universes where the laws of physics are completely different from our own, where time flows in strange directions, or where matter and energy obey rules unimaginable to us. Every possibility that can be described by mathematics exists as a universe in this ultimate reality. Other models describe paired universes or twin universes to explain puzzling features of our cosmos. One such idea attempts to solve the mystery of why there was more matter than antimatter at the birth of our universe by proposing the existence of a mirror anti-universe. This mirror would contain particles opposite to our own, balancing the cosmic scales. Another two-universe model suggests that the tension surrounding the Hubble constant, the rate at which the universe expands, might be explained by interactions between our world and a parallel twin. In this mirror world, every fundamental particle we know has a counterpart. Still another variation, sometimes called the bi-world model, tries to solve the mystery of dark energy and the cosmological constant. In this view, two interacting universes each hold enormous energy values, but when combined, they share a much smaller effective energy that resembles what we observe in our own cosmos. Some multiverse theories even imagine an infinite chain of universes, each born from the death of the one before. These cycles can be seen as a repeating pattern of big bangs followed by big crunches or big bounces, where the universe contracts, collapses, and then explodes into a new beginning. In such a vision, universes do not exist all at once, but arise one after the other in an eternal sequence. The building blocks and laws of nature may shift between these cycles, leading to entirely new forms of reality. Within the grand mathematical structure of string theory and its higher dimensional extension known as M-theory, there are even more exotic visions of the multiverse. These frameworks require 10 or 11 dimensions of spacetime instead of the familiar 4. The extra 6 or 7 dimensions could be curled up into spaces so small we cannot detect them, or our own universe might be locked onto a 3-dimensional sheet called a D3 brane. If this is true, there could be countless other branes nearby, each carrying its own universe with its own history. Black hole cosmology provides yet another possibility. This view imagines that our observable universe is actually the inside of a black hole, one among countless others existing in a much larger universe. In this framework, white holes, the opposite of black holes, also play a role, spewing out matter and energy into new universes beyond our own. All these theories of the multiverse share one deep purpose: to explain why our universe appears so perfectly balanced for life. The laws of physics and the constants of nature seem tuned in such a delicate way that if they were even slightly different, stars, planets, and life as we know it could not exist. If, however, there are countless universes, each with its own laws and constants, then it is no surprise that one of them, ours, happens to have the right combination to allow life and consciousness. This reasoning is linked to what is known as the weak anthropic principle. We can only find ourselves in a universe that allows beings like us to exist, because in all the others, observers would never arise. Although this may sound like a modern idea, a form of this reasoning was present in the mid-19th century. In the year 1844, the philosopher Arthur Schopenhauer wrote a work titled Von der Nichtigkeit und dem Leiden des Lebens, or On the Vanity and Suffering of Life. In it, he argued that our world must be the worst possible of all worlds, for if it were significantly worse in any way, it could not continue to exist at all. His view, though stark, echoes the same sense of inevitability. We live in this world, and not another, precisely because it is able to sustain itself and those who inhabit it. Supporters and critics of the idea of multiple universes have long argued over how the principle of Occam's razor should be applied. Occam's razor is the philosophical tool that says the simplest explanation is usually the best one, the one we should accept unless there is strong evidence otherwise. Critics of the multiverse concept say that suggesting an almost endless number of unseen and unreachable universes, just to explain our own, goes directly against the spirit of Occam's razor. They argue that multiplying possibilities without proof makes the idea unnecessarily complicated. But those who defend the multiverse argue differently. They claim that if we measure simplicity not in everyday terms, but in terms of Kolmogorov complexity, the mathematical measure of how short a description can be, then the multiverse is actually the simpler option, compared to believing in one lone, very unusual universe that stands by itself. One of the most passionate defenders of this view is physicist Max Tegmark. He explains the principle with a comparison that anyone can understand. He says that sometimes a whole collection is actually much simpler than one of the individual things inside it. This idea can be stated more formally using what scientists call algorithmic information content. That concept tries to capture how much information is needed to describe something. In practice, it means you look at the length of the shortest possible computer program that can generate whatever number, pattern, or object you're talking about. Tegmark gives an example with numbers. Think about the set of all integers, meaning all whole numbers stretching out forever. Which is simpler, describing all of them, or just describing one? At first glance you might say one number is easier, because it seems smaller. But in fact the whole set is simpler, because a tiny computer program can generate every integer, while describing just one very large number might take pages of digits. From this perspective, the set of everything is actually easier to describe than a single part of it. Tegmark extends this reasoning to the multiverse. He says that the higher levels of multiverse theories make reality simpler, not more complicated. In his explanation, moving from our single universe to what he calls a level 1 multiverse eliminates the need to specify the starting conditions of our universe, because all possible conditions exist somewhere. Going further, the level 2 multiverse eliminates the need to carefully explain why the physical constants in our universe are what they are, since in that framework different universes naturally have different constants. At level 4, one does not need to specify anything at all, because every possible mathematical structure exists as a universe in its own right. According to Tegmark, in each of these steps the multiverse actually removes the need for extra assumptions. He points out that the most straightforward and arguably most beautiful theories naturally include parallel universes. If someone wants to deny the existence of other universes, they actually have to complicate matters by introducing unsupported ideas, such as space being strictly finite, or the mysterious collapse of the wave function, or strange asymmetries that are not backed by evidence. In his words, the choice comes down to this: do we prefer many worlds or many words? And perhaps, as he suggests, human beings may one day grow more comfortable with the strangeness of the cosmos and even learn to see that strangeness as part of its beauty. Beyond questions of elegance and simplicity, there are deeper puzzles about which universes might actually exist. In any grand collection of possible universes, whether described in terms of histories, physical variables, or mathematical structures, not all of them may ever become real. Some might remain only possibilities, while others might be realized again and again. For instance, in certain theories that imagine time stretching on without end, there could be infinitely many universes, yet only a very small fraction of those might contain the right conditions for human life, and perhaps only one of them might lead to the particular history of Earth that we know. According to one suggestion, a universe that gives rise to life as it exists on Earth is radically unusual, It is non-ergodic, meaning that out of the nearly limitless variety of organisms that could be possible, only a tiny fraction will ever actually appear. Other scientists and writers imagine the opposite picture. In their versions of the multiverse, the different universes are not wildly different, but instead strikingly similar. In that scenario, humanity exists in many universes at once, each equally real, but with different variations of history. In one, everything may have unfolded just as it has for us. In another, certain decisions, events, or outcomes might have gone differently, leading to branching versions of human experience that run in parallel. This picture captures the imagination because it suggests that every choice and every possibility could play out somewhere,